check, 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 check.
technological tools and stage interpreter, and types and meta theory. That's more POPL classic. And finally, micro lenses, and in particular at the end we have a panel, okay, discussing semantics-based transformation in the age of LLMs with invited panelists. Okay, with that, this is the most exciting part. We have three excellent invited speakers with really diverse, interesting topics. William Bowman, and Brittany is not here yet. She has other things to run, but anyway, she's in here. And Sat Dan Sim, okay. And the topics are so exciting and so diverse. That's what PEPM is great. So here's just over a program. You can see it. There's a break and there's a lunch. Okay, we have to go figure out. I think lunch will be on the 3rd floor after some turns. Okay, we're really far. And then in the afternoon, at the end there was a discussion. There's also a break. And in the evening, there's this Jane Street has game night and food. Okay, so at 5:30 we'll finish, and there was half hour we can chat around for people who are not able to go anywhere else, and we can also go to game night. Okay, and finally, thanks to everybody to make anything happen. Okay, pop organizers, SIG plan, different people that help in all the ways. PC, of course, reviewing the papers, and steering committee tell us all the histories and advice, and of course the authors who write all these diverse, interesting papers. And of course, the invited speakers that will start the really even more difficult. Oh, here's Brigitte. you're the only name that I'm missing. It's like the very end. Don't go to the second part. Yeah. Yeah, and then this is very end. We were led by the volunteer. Yeah, and of course, thanks for everybody who are attending, right? These are the ages, especially starting with class and so on, and people have to attend online, some of them, and for people who make the effort here in such cold weather. Okay, so we have indeed one remote presenter in the morning and one remote person in the afternoon, but everybody else is here. Okay, so let me introduce Sam, who runs the first session, who will introduce invited speaker.
Thank you, Annie, and thanks for putting together such a great program. Well, it's my pleasure to introduce the first keynote speaker, who is Satnam Singh. I recently had him over at Edinburgh giving an excellent distinguished lecture. Is that good? Great, we can see your slides. Can you hear us?
Yes, I can hear you. Can you hear me?
Yep, we can hear you. So go ahead.
Perfect. So, hi everyone. My name is Sune. Wait, just give me a second. I'll have to. There's some echo, so I'll have to turn it down. I think that's good. So, hi everyone. My name is Sune. I'm one of the authors of a type-safe calculus for generating syntax-directed editors. And with me, I have some of the other authors who will also be available at the Q&A session later. So first off, I want to briefly introduce structure editors. So they were introduced in order to avoid syntax errors by letting us build the abstract syntax tree directly, while also putting constraints on how the tree can be edited. And this also offers the benefit of letting us skip the parsing process. In terms of early work, we have Reps and Bau, who introduced the Cornell program synthesizer in 1981 for the PLI language. And in 1983, they presented the synthesizer generator, which can generate a structure for any programming language on the basis of a language definition. And Omar and others developed.
Can I just interrupt?
The Hazel programming environment.
Can you hear me?
And with Hazel comes an editor calculus, which is a language for specifying edit operations. And here I want to note that Hazel itself is not a structure editor, but it introduces the notion of the syntactic holes, which inspired the foundation of our work.
Do we have a way of communicating?
And the foundation of our work is the type-safe structure editor calculus, which has been developed in a series of student projects at the University of Copenhagen and Aalborg University. And the calculus was first implemented by a group of students at the university.
Apparently.
And this talk presents a generalized version of that calculus and also an encoding into a typed lambda calculus. And this has two significant advantages. The first being that the encoding satisfies a general property of type safety, such that if well-typed, well-typed editor scripts will always produce syntactically well-formed programs. And also it becomes possible to devise an editor generator in a typed functional programming language. So the highlights of our work is the encoding.
Er det meningen, din slide skal skifte?
Yeah.
Can you hear me?
Your slide is just the same.
Oh, shoot. Thank you for pointing that out.
You can see we can see the new one now.
Should they be able to?
Okay. So it seems like when I go full screen, it doesn't follow. Okay, I'll keep it like this. Thank you. Yep. So okay. So I showed you some slides before. So this is from the Cornell program synthesizer. This is from Hazel. And here we have the type-safe structure editor calculus. So yeah. I think that this is almost where we got to, and then I mentioned that what our work is, and this is where I came to it. So the highlight of our work is that is the encoding and the proof of its soundness, and also an implementation in Elm of an editor generator based on the encoding. And our criteria for a good implementation are that we want to edit the abstract syntax of any program directly, and we want generic editing in the sense that we want to be able to edit the program of any given language given by its abstract syntax. We want to be able to handle context sensitive syntax. and we want multiple views of the code being edited, say, for example, a tree structure or a pre-printed view. And lastly, we want a non-challenging way of specifying the abstract syntax. And we also demonstrate the generality of our approach by showing how to handle 3 different language specifications. So we use the denotation by Harper to represent abstract syntax trees, where they are defined by a collection of sorts, a family of operators, and a family of variables. So let's say, for example, we have a small language with simple arithmetics. So we might have a set of sorts which only contains expressions, and then we have, let's say, a plus operator which has this arity, which should be read as the plus operator takes 2 arguments of sort expression and expression, and it returns an expression. But often a syntax will include binders. So following Harper, we can represent the syntax with binders by enriching the ASTs with bindings by assigning operators with a generalized arity, where this should be read as where this should be read as a vector of variables of sort x1 being bound to the argument of sort x1. So following up on the simple example from before, we can now extend it with a sort statement, and we can have a let operator which takes an argument of sort expression and statement, where the second argument binds a variable of sort expression within its scope. And now I want to present an editor calculus for an arbitrary abstract syntax. So assuming that we have an abstract syntax given by a set of sorts and a family of operators and a family of variables, then for every sort, we want to add a whole operator, which allows us to insert syntactic holes representing either empty or missing subtrees. And we add a cursor operator, which tells us where the editing currently takes place in the syntax tree. And our generalized editor calculus is defined by these formation rules. So first of all, we have the edit actions, where we have the prefixing, where the prefix pi can either be the child n operator, which moves the cursor down a level to the nth child, and we can move the cursor up to the parent, or we can insert an operator. And then we have conditionals, where if the condition is satisfied, we execute E1, and if not, we execute E2. And these conditions can either be negation, conjunction, disjunction. And we also have a model logic which can tell us whether the cursor is currently at an operator encapsulating some given operator, if some operator exists in some subtree, or if the operator exists in all subtrees. And we also have, unlike the Hazel editor calculus, we also allow repetition-based editor scripts using recursion. And also the conditions allow us to make edit actions conditional on the shape of the abstract syntax tree. So having the editor calculus, let's dive into the definition of the trees that we want to edit. So we first define trees without cursors, and these are crucial for defining cursor contexts and well-formed trees, which I will come to in a second. But essentially, the sorts here are made up by the sorts given by the abstract syntax, and the operators are made up of all of the operators from the given abstract syntax, excluding the cursor operator, of course. And then we have cursor context, which holds information about the current tree surrounding the subtree where editing takes place. we represent the cursor context with an additional sort C, and the subtree that contains the cursor is represented with a context hole operator. And for well-formed trees are trees with only a single cursor, and the cursor itself is essentially just one more operator, where which is added here in step 2 to represent the cursor currently encapsulating the root of a node, or either any of the immediate children of an operator. The semantics of the editor calculus are defined as small step semantics. I will not be presenting all of them, but here are some. So for example, we have conditionals. So if an abstract binding tree or APT satisfies phi, then we will execute E1, and the abstract binding tree will remain unchanged. And I also want to note that this notion here represents an abstract binding tree and the cursor context within it. And we also have, of course, if an APT does not satisfy phi, then we execute E2, and the APT remains unchanged. And then we have contexts. So given a prefix pi, if pi transforms an APT into a prime, then prefixing an editor expression with pi will result in E with the transformed APT. And then we have a substitution and cursor movement. So for insert operations, so given some operator and an encapsulated cursorless APT, which you can see by which is denoted by the hat here, then applying the insert operation will replace that APT with the given operator, where every argument has where we insert a hole for every argument for that operator, and this implies that the sort of the encapsulated APT is of sort S, which should be the same sort of the given operator O. And we have child operators, which, as the name implies, if we are encapsulating an operator with n children, we can then move to the ith child of that operator. And then we have the parent operator, which of course does the opposite. So if we are encapsulating a child of a node, then we can move up to the parent. And then we have the conditionals. Here I will show a couple of them. So let's say that if an encapsulated APT does not satisfy phi, then the encapsulated APT does satisfy phi negated. And we have conjunctions such that if an encapsulated APT satisfies phi 1 and phi 2, then that means that the encapsulated APT satisfies the conjunction of phi 1 and phi 2. And then finally, we have a model logic. So if we are currently encapsulating some operator O, then we satisfy the at O operator. And we have this diamond, which tells us whether an operator exists in any subtree. So let's say that an encapsulated APT AI satisfies diamond O. Then also the parent of this APT, let's say that is encapsulated by the cursor, then diamond O is also satisfied. And of course, we have that if an encapsulated APT satisfies at O, then diamond O is also satisfied. So having the generalized editor calculus, we will now show how to encode it into a simplified lambda calculus with pairs and pattern matching and recursion. And assuming that the type system of the simplified lambda calculus is sound and that the encoding is correct, then any instance of the editor will have the sound type system. And here are some of the terms and the types of the extended lambda calculus. So here we are able to represent the operators from our abstract syntax. And we also by types, we have function types, and we have the sorts from our abstract syntax, and product types, and booleans. And the types of the operators can be deduced from the arity. So having the typing rules, we can then encode the APTs the following way. And lastly, we also have encoding rules for all of the editor expressions. So having the editor calculus and the encoding, I will now talk about the implementation. So where some of the important choices concern how we represent the syntax, whether we want code generation or a generic model, and how we generate the source code and how we implement the editor expressions. So in terms of early work or simply other work on abstract syntax specification, we have Metal, an early formalism presented in the 1980s. And we have the CFIR ASDL, which is also an early example, which stands for Abstract Syntax Definition Language. And we have Abstract Syntax Notation 1, which does have abstract syntax notation in its name, although it has primarily other use cases, such as transmitting data structures over the network. But all of these have a common problem, which is that they don't support binders. So for this reason, we decided to create our own specification language. And here I have a subset of an SQL dialect, where we have our sorts at the very top. So we have queries and commands and so on. And down here we have our operators, and we have their arity, and we have their terms, which would be used for, let's say, pretty printing, and we have the sorts. And also we want to be able to parse such a specification language. So we also created a more computer-friendly and parsable version of the specification language. Now, a question we stumble upon is if we should use a generic model or if we should generate code for an editor instance. So one of the upsides of having a generic model is that we don't need any code generation, which arguably is less work and less error prone. But this is less efficient, and it needs a lot of well-formed checks written manually. However, on the other side, we have code generation where we can take advantage of algebraic data types, which can constrain us to only be able to create well-formed terms. However, this requires code generation, and it is hard to guarantee that the generated code always works. And we also notice that this question relates to the question of specialization in the work of partial evaluation. So we decided to go with the approach of generating source code. And for this, we used a package that was already built beforehand, which was very useful when integrated directly with the language specification parser. And here we have an example which looks a little bit like something that we wanted. So let's say that we have a sort statement, and we have which has and we have operators, assignment, statement from home, turn, and so on, which takes argument. For example, assignment might take an ID and then expression. So we can sort of parse this information from our specification language, and then we can generate actual working Elm source code from that. I am running out of time, so I will jump over this quickly. Here we have we had a simple, not a simple, but we had an ambiguity in how we actually want to decompose AST. So we found a way to always decompose these AST as in exactly one way to get exactly one cursor context and one well-formed tree. And finally, we wanted to pick a good set of languages as examples, and we ended up with C, SQL, and text, since they are languages of different paradigms and purposes. And yeah, here I had some examples of how one can easily introduce syntax errors in C programs and in SQL queries and in text documents. And finally, here I have a screenshot of a working generated editor for the SQL language. And yeah, so in conclusion, we have presented a general editor calculus and shown how to encode it in a type lambda calculus, and we have an implementation. But some of the editor expressions are yet to be implemented. So we still need to handle context-sensitive syntax, and we need to implement views of the code being edited. So for future work, we want to finish the implementation, and we want to consider a more concise implementation. And this could maybe be in Haskell. And that was all from me.
Can you hear me?
Yes.
Excellent. All right, let's thank the speaker. I don't know if you can hear us, but
I can.
There was lots of applause there, even if you couldn't hear it.
I couldn't think.
Okay, yeah, we have plenty of time for questions. So does anyone have any questions? Okay. Well, I'm going to start off by asking you... you had a future work slide there. This seems like a nice basis for building these editors. How do you see this having practical impact? Is this going to influence the design of systems like Hazel, for instance?
Do you mean the creation of a syntax directly structure editor like this, or do you mean going with a different implementation? I'm not sure if I'm
wondering, is this going to change the way in which people are actually building these kind of systems right now? Or is it just an academic exercise?
Well, I honestly don't have a good answer for that. If some of the others, maybe Hans would like to chime in, I could imagine.
Oh, wow. Here I am. Hi, I'm Hans. I'm co-author of this, and I think if I were to say something, I would probably say that, I mean, this grew out of the same ambition as the synthesizer generator and the metal framework from INRIA back in the 1980s, namely to see if one can identify common principles for editors. So maybe one could imagine using this for a generator, but then one would need a lot of optimization to do this. But I think it's also got to do with the fact that, well, it would be nice if we could have a workbench for experimenting with programming languages in this setting of editing. Does that answer your question?
Can you still hear me? Yes, it does answer my question. We now have another question.
Thank you for the talk and the work. I don't know if they see us, but anyway, I'm Annie Liu, and I happen to have used the synth generator for my PhD thesis. But since then, I haven't followed very closely with these editor, programming or creation. So are these new editors also generated from these from grammars or whatever types, or they just manually written based on some languages or their keywords? You may not, I assume, right, not to the based on the type size you did, but for all these practically used editors, right? People use a lot of them for JavaScript to just put a thing on the web. So how are they created now? Just manually programming each little thing?
Do you mean in terms of our implementation, or are you asking like for structure editors in general? I'm not sure if I'm following.
Just in general, right? Because how about the future? I mean, future everybody using these editors written JavaScript on the web, right? That's the current. So, but are they writing in any principled way, or what I'm saying, just ad hoc programming?
Yeah, I am not sure of how it is going on in the real world with structure editors right now. I have not researched how that is going. If some of you other guys have anything to chime in with, that would be nice.
I'd like to say something here.
Oh, sure, go ahead.
I would say that a lot of the work that we've been doing here in this work is really got to do with the back end. Really, as you can see in Suna's presentation, the graphical interface, well, there isn't on at present. A couple of years ago, I supervised a bachelor's project here in Copenhagen that was mostly working on the front end. But I think the front end would have to be very specific for the concrete syntax that you're after. We're dealing with abstract syntax and whole backend machinery. I think one would have a different pretty printer for each of these settings, really.
Okay, all right, thank you. Yeah, this is more abstract.
We're going to have one more question. And yeah, before I forget, the coffee is upstairs after this.
But not for us.
Well, you have to find your own coffee, yeah.
Kenichi Asai from Ochanomizu University. I think this editor is for avoiding syntax errors. And I wonder if it can be also used for avoiding type errors.
I think that's a good question for one of you guys that worked on that part.
Yeah, I think the type system that we've got deals solely with making sure that the syntax tree is well formed. But my guess is that one could, I mean, if we think of attributes, we could annotate the AST with attributes and prevent type errors in that way, couldn't we? The attributes being types. I mean.
Hi, yeah, thanks for the talk. I have one question. So there's like been a recent interest, I guess, in editors for like collaborative editing. And there's a paper at POPL this year on Grow, which is like a Hazel collaborative editing sort of framework. I'm wondering if you've thought about how to extend your calculus to distribute like, or if that's kind of just like out of scope for now. It's a lot of work, so yeah.
Well, my take on that is that very early in the process, we designed this to only support one cursor. So yeah, that would be my answer. That no, we were not really looking into collaborative editing in this project.
No. I think one thing that might be making this a bit more complicated is that then we would have to go to redefine the translation, because one thing that's really nice about this work is that one can translate the editor calculus into some type lambda calculus, and that makes sure that everything's nice and sound.
Okay, thank you very much. We need to wrap up now because we're out of time. But thanks a lot for the talk and for your answers.
So, welcome to the second session of PEPM. So, it's nice to see that so many are interested in hearing the talks in this session. And the first talk is an invited talk by William Bowman. So, William is comes from Vancouver, and he's generally interested in using also types for better compilation. And today he will talk about the ethical compiler. So please go ahead.
Thank you very much. We have the mic switched on. Okay, hopefully people. Okay, that sounds better. Okay. Good morning, everyone. So on Saturday, I was having my morning coffee. I was thinking about POPL logistics, what to pack, when do I need to arrive, that sort of thing. Thinking about how to start this talk. I was a bit stressed. It's quite an unusual topic, ethics and compilation. It's a bit outside my comfort zone. I don't have any proofs or theorems to show you. It's a bit provocative, trying to convince people to think very differently, think using humanities methodologies rather than our normal science methodologies. It's a bit of a risk, but I thought it was worth doing. So I was having my coffee when I hear my neighbor upstairs let the water out of their bath, followed very quickly by water hammer in the wall, gurgling coming from my kitchen, and some rattling around in my sink. So I run to my kitchen, and I start bailing water into my bathtub. The water from the whole building was coming up from the drain into my kitchen sink. It was filling up very fast. I imagine there was enough water to fill a bathtub. This water was beyond foul. There was bits of decomposing food, there was grease, there was globules of fat in it. The smell was indescribable. It got all over me, all over my pajamas, all over my kitchen, all over my bathroom. I felt like I would never be clean again. Eventually, the weight of the water caused my sink to drop out of its frame. Thankfully, somebody had anticipated this, and there were two metal brackets underneath the sink, so it didn't drop very far. But the seals on one of the pipes burst. So now one side of my sink was filling up, and the other was just leaking into underneath the sink. So I put another pot there. I was bailing water, a pot in each hand, for about 15 minutes before the water slowed enough that I could call emergency maintenance. I kept bailing water for another hour before a plumber arrived. Whenever there was a lull in water use, I'd empty the pot underneath the sink and go back to bailing. Anytime anyone in my building used the water, it would flow down their drain and then back up into my sink. I just kept praying nobody would use the shower or worse, take another bath. So I'd been bailing water for about 2 hours before the plumbers finally found what the problem was and deployed a workaround. So by this time, my arms were shaking. I hadn't even had breakfast. My forearms are still sore today. The problem was what are called fatbergs. There was 12 feet of solid grease that had been slowly and then very suddenly clogging the main connection for my entire apartment building. And I was last in line, so it was backing up into my unit. They spent another 3 or 4 hours fixing the problem. They used this fancy drain snake machine, which had a camera and some attachments, and they broke up the grease and scrubbed the pipe. The senior guy showed me a video of some of it, and I asked him, will you send this to my building manager so, people know, don't dump grease down the sink? And he said to me, in the tones of a man who had done this 1,000,000 times and would do it 1,000,000 more, with no judgment, a simple statement of fact. People never listen. And he went back to scrubbing the pipes. This plumber, he was probably 50, maybe 60 with a good moisturizing routine. He was certain that people knew what they were doing was wrong, and they were going to do it anyway. Well, I'm only 35. So let's talk about ethics. So today, we're going to talk about ethics, but I don't mean big ethics. I'm not going to teach you how to solve racism in your compiler. I don't even know what that would mean. That's not in scope. We're going to be doing small, common, overlooked ethics. And in fact, we're going to look at some ethical dilemmas that actually have to do with harm. But some of these aren't really about ethics. Some of this is metaphorical ethics. We're using ethical thinking to approach certain kinds of problems in compilation. The first question that we'll be asking is this one. We'll start here. This is the ethical question I want to answer. This is the opening line to one of my favorite papers. This is from Finding and Understanding Bugs in C Compilers, the C. Smith paper. It's a very subtle statement. It feels so true. But what does it mean? What are compilers? And what does it mean for them to be correct? And what is this should doing here? What does this mean? I'm not going to relegate the meaning of the verb be. You can see prior work on that. Let's start with compilers. What are compilers? So here's the compiler's alignment chart. Everyone on this chart agrees that a compiler is a transformation from one thing to another. Then they stop agreeing about the details. I think in the context of this audience, I can safely say that a compiler is a transformation between programming languages. I hope I can say that. I'm not going to define programming language. So a compiler is a transformation between languages. Any program in the source is transformed into a program in the target. But when I think about compilers, this is not the only thing I'm thinking of. I'm also thinking about all of the other stuff that goes into building and supporting a compiler. Mathematical models of programs, manipulation and analysis tools, interpreters, error reporting, methodologies. All of these things support a compiler, and all of them should be correct. So what is correctness? What does it mean for a compiler to be correct? This is a slightly harder question to answer. It's still an active area of research. Here are a couple of definitions. We might mean whole program correctness. I have a whole program in the source. I could interpret it and get a value, or I could compile it down and then run it and get another value, and those values should be the same. I might mean separate compilation. I have two components in the source language. I could link them, run them, get a value, or I could separately compile, then link, and I should get the same value. Or I might mean compositional correctness, where I have a source program that can directly link with a target language program. Think something like C linking against an assembly blob that may have been generated, may have been handwritten. I should be able to link these, evaluate to a value, or compile, then link, and get the same value. Or I might mean full abstraction, where I have two components and they are indistinguishable. They should be compiled to indistinguishable components. And if I have indistinguishable target language components, they should have come from or have some equivalent to indistinguishable source language components. So here's a bunch of options. And when I say a compiler should be correct, which should I use? Oh, there's that word again. Let's ignore that for now. I could make arguments. I could tell you all the reasons rockets will explode and X-ray machines will turn into lasers and rock proofs will go wrong if I don't choose one or the other of these theorems. Here's how these arguments go. Well, real programs are not monoliths. You should expect that you get some guarantees when you link with something. So we probably don't want whole program correctness in general. But depending on the language you use, maybe you're okay with separate compilation, maybe you're in Haskell, and you really only expect guarantees if you link Haskell things. So you'd consider that the GHC compiler is correct, even if you should only get guarantees when you link with Haskell. But if you're working in C, you probably expect to get guarantees when linking with arbitrary assembly stuff that you don't know where it came from. So GHC should give you guarantees when linking with something else, like compositional correctness. Very few people know or care what full abstraction is, and even the secure compilation community is debating whether it's the right notion. So we probably shouldn't use that one. Anytime I try to explain compiler correctness, I run into this word, should. I can't even see it as a word anymore. It's just a sequence of letters. What does should even mean? And this is the hardest question of all. We've been preoccupied for about 60 years now, trying to create correct compilers, all the while making claims about should. So what does should mean? To answer this question, we need something else, something outside of correctness. We need something like ethics. So let me say what I mean by ethics. Should in English is quite overused. We use it a lot in inappropriate ways. Typically, it means something about obligation. To be a little more precise and make it very clear that I'm not being colloquial, I'm going to use ought as my ethical word. To say something ought to be true is a different judgment than to say something is true. Is an objective statement of fact in the world. Ought is an ethical judgment, a subjective claim about your values, your morals, your beliefs. What Hume argues is that it's actually impossible to derive ought from is. You cannot derive an ethical judgment from pure rationality. This is an old result. Not everyone believes this, but I tend to agree with Hume here. And that means if you want to derive an ethical judgment, you need some ethical axioms, your most fundamental values, beliefs, etc. Now, I'm not going to tell you what to value, or if you have many values, how to weigh them against each other. There's about 10,000 years of prior work on that. I'm only concerned with how we make an ethical argument. So for example, the following is an invalid derivation. Bugs in software cause harm. types reduce bugs, therefore one ought to use a typed language. This doesn't follow, because maybe I actually like causing harm, and so I should use an untyped language. But we can make it valid by admitting some ethical axiom like, I believe one ought not cause harm, right? As long as we ignore all the other ethical implications of software. Okay, so that's ethics. Now we have everything we need to know to deconstruct this statement, right? We know what each of the bits mean. We know that this means a transformation between languages is morally obliged by someone's system of ethics to satisfy some correctness theorem. This is a slightly strange statement. It is relative to somebody and their system of ethics, their values, and it also requires picking a correctness theorem. So, can somebody give me a system of ethics and a correctness theorem that makes this true for anyone who uses your compiler? I doubt it. I conclude the opposite, that actually, in general, this statement is unsatisfiable, and compilers shouldn't be correct. Ignore 60 years of research, ignore all of my own papers, down with compiler correctness, I say. Okay, less pithily, what I mean is that compilers either are or are not correct with respect to some correctness theorem, but to make a judgment about whether they ought to be correct requires connecting someone's values, their system of ethics, to truth statements about programs. And this cannot be done without first fixing a subject and their system of ethics. So we cannot make claims about whether a compiler ought to be correct without some ethical axioms. And no matter what choice of compiler correctness theorem we choose, we will violate some ethical axioms in general. So consider this example. I have a program E. P ought to be true of E. I value P in some way. E runs to V. I compile E. P is not true of E prime, my compiled program, but E prime still runs to the same value. Is this compiler correct? And is it ethical? So we know now we need to say, well, is it correct with respect to what theorem? And is it ethical with respect to whose values? And no matter which theorem I choose, I can make this compiler unethical. It will generate a program that does not behave as it ought. Because any choice of compiler correctness theorem is going to impose values on the programmer. It's going to impose the compiler writer's values. If I choose whole program correctness, I'm saying the only thing I value is the evaluation behavior of the program, right? That it runs to a particular value. But that might not be what the programmer values. This is a form of moral universalism. So compiler correctness ignores the programmer's values, their intent, what they think ought to be, and imposes the compiler writer's values on them. And in general, I think that moral universalism, saying that a single system of ethics and values is going to work for everyone, is metaethically wrong, at least in the context of compilers. And therefore, compilers shouldn't be merely correct. So I would like to stop thinking about compiler correctness. Instead, I want to think about ethical compilation. What does it mean to preserve what ought to be true? An ethical compiler would be one that preserves values, the intent of the programmer, how the output program ought to behave. Intent isn't exactly the right word. It's not a great fit for ethics, but it's the one I've chosen, so I'm going with it. Now, ethical compilation, phrased this way, raises interesting research questions that are distinct from compiler correctness. The first of which is, well, how does the programmer express their ethical axioms, their values in your program? Once you have those, how does a compiler preserve them? There's been a lot of work on how do you preserve the true behavior of the program, but we're now focused on what was the intended behavior. And now that we have these two judgments, intended and true behavior, how do we reconcile the two when they don't match or when they do? I think ethical compiler correctness or ethical compilation already exists. And there's been a lot of research on it, perhaps intentionally, perhaps not. And I'm going to spend the rest of this work recasting a bunch of work through the lens of ethics, and hopefully deriving a recipe by which we can design and implement more ethical compilers. I think there are sort of three broad categories of work. The first is on expressing truth and intent. And anytime we're looking at an expression problem in programming languages, it's going to be in one of these spaces. We're going to have ought space. This is where a lot of our stuff lives. We're trying to express intent, values, axioms. These are things like types, pragmas, logics. And then there's is space. These are just true things about program, true statements about programs. These are things like semantics, analyses do this, inference does this, right? And we want to be very clear which space we're working in and how we're expressing and what we're trying to express. And then in the middle, the two should meet, and we're going to reconcile the two at some point. Once we actually have intent, we need to understand how do we preserve it through compilation. And there's been relatively little work on this. And then finally, I'll talk about some of the implications of trying to resolve ought and is, truth and intent. Okay, so here's a quick spoiler. Here's my 6 meta-ethical dictums of ethical compilation. First one that we've already seen. Compilers should be ethical rather than correct. I've already made an argument for that. I'll make arguments for the rest along the way. So programmers should be able to say whether something that is ought to be. This is a mistake that comes up a lot in semantics. Anything that ought to be should actually be possible, right? This is about resolving the is versus the ought space and expressing which one we mean. Then preservation. What ought to have been still ought to be after compilation. Last 2 are about reconciling is against ought. So we should never infer ought from is. This is the is-ought gap, Hume's is-ought gap restated about inference. And finally, one should always reconcile is against ought. And this is largely about communicating to the programmer violations of their expectations. The theme of all of these is how do we navigate the is-ought gap in an ethical and useful way. Okay, so if we're going to produce programs that behave as they ought, then we need to know how to express what they ought to do. Over on is space, is our objective judgment, so our objects are programs. Certain things are true of programs. Over in ought space, we have a subject. The subject is the programmer. They have values, they have intent, they believe certain things ought to be true of their program. For example, E runs to a value is true, V has type A, that's true, but maybe the programmer believes that E ought to be secure in their context. Let's look at a concrete example. So this is one of my favorite papers. This is the correctness security gap in compiler optimization. This is kind of the closest thing to studying the is-ought gap that I've seen. But they frame it in terms of correctness versus security, as if these things are at odds. And it's quite telling that they think these things are at odds. The context they're working in is C programs, right? So they have a C program, and they have a bunch of properties of C programs. For example, C programs might overwrite secrets in memory, trying to remove them from memory in case there's a bug, in case there's a security issue. But the compiler removes these writes, as it should, because C says dead writes are not observable. So the compiler is completely correct in doing this. But if you're a cryptographer, you ought overwrite these secrets in memory because you don't want them leaked if there's a bug somewhere else. And you believe that the compiler ought to preserve these overwrites. So the compiler is behaving unethically, according to the things you value. So if you're doing compiler correctness, you just say, this is not a bug, working as intended, go away. Right? All of this is perfectly correct. And that is often the approach that people take in C. They say things like, oh, why don't you just memorize the ins and outs of the C semantics or the particular behavior of your compiler? Maybe if you're desperate, you can heavily obfuscate your code so the compiler doesn't realize you have dead writes here. Or, of course, the most common answer, just write it in assembly and don't use a programming language, which is certainly one approach if you're a 10x C programmer. The alternative view, put quite succinctly by a security researcher I know, is that actually the compiler is immoral and it must change. And it must change in 2 ways. First, we need the ability to express that the dead store is intended. It ought to be there. I value this dead store. And second, in is space, we need to make a semantics where it is possible in truth for dead stores to exist. And we need both of these. So that's actually exactly what De Silva et al. Propose, right? And exactly the sort of formula I would have suggested. They say we should add a keyword to C that expresses these pointers, dead stores to them are observable, and we need to change the semantics to make that possible. Okay. If we omit any of these 2, then we get something that's still unethical. For example, we could just say change the C semantics so dead writes are observable. But now all we have is a compiler that behaves in some way, not as it was intended to behave, right? There are going to be programmers who value getting rid of those dead stores, who value high performance C code, right? They no longer get a program that behaves as it ought. Although the cryptographers get programs that behave as they ought. So we can't just say all dead writes are observable. We also can't just say, well, we'll add this keyword and not concretely define exactly what it does. It's a little weird to think what this would even mean in this context, but actually, if we look at things like type systems, this happens all the time. So we can't just say, oh, now you can express your intent, but we have no guarantees about what that intent does in truth. So we need both of these things. The programmer needs to be able to say, over in ought space, whether something that is ought to be, and down in is space, if we express something ought to be, it should actually be possible. Right? These are our first two meta-ethical axioms. Now, we could go on adding keywords and stuff to our language. Actually, that's what the paper suggests. That seems very popular in C. But my favorite way of expressing intent is with types. Types are a great way of expressing intent. Our ethical axioms are values, as long as they come from the programmer. I'm quite opinionated about my type systems. In a bidirectional system, for example, this is very clear that types kind of express ought, because we have two judgments. We have the check judgment that we're saying E ought to have type A, and I'm going to check that fact. And then we have the synth judgment, which says, from E, infer what its actual type is, or synthesize its actual type. E does have type A. And at some point, we have to reconcile these two against each other. If we just use, say, complete type inference, we only get the is part of this judgment. Okay, so let's see an example of expressing truth and intent with types. This comes from my own work, trying to add dependent types to low-level languages. This is my work with Adam Geller, my PhD student, and Justin Frank, who was an undergrad at the time, is now a PhD student at Maryland. And what we were looking at here is WebAssembly programs. So our objects are WebAssembly programs. We wanted to be able to statically verify that no bounds checks were necessary at runtime. We needed no dynamic bounds checks. However, the WASM semantics say all possibly unsafe instructions require a dynamic check at runtime. So the compiler inserts these, and the compiler is completely correct to do so. But if I'm a WASM programmer working in certain contexts where these checks become expensive and the VM guard page's tricks don't work anymore, I look at this code and I say, well, this is memory safe. This ought to be memory safe even without the dynamic checks. So the compiler is doing something I do not want, right? It is behaving unethically. So how do I resolve this? And I thought back to old work on dependently typed assembly language, DTAL. Well, we can add a simple type system, a simple dependently typed type system that statically verifies none of these bound checks are necessary at runtime. And that's in ought space, but that's not enough. We also need the new semantics that say, well, after you type check this instruction, you're guaranteed to not have a dynamic check. That's in is space, right? So now I can have a program that behaves as it ought. And if I had only done one side of this equation, say, add some kind of type system over WebAssembly, I can verify memory safety, but I get no guarantees out of my compiler, right? And vice versa, if I just work in is space, I say, oh, we'll do a static analysis and try to optimize away these checks in the general case. I will miss some of them, and I am unable to express these particular checks ought not be there, right? So I need both sides of this if I want to do ethical compilation. There's plenty of work to do in either of them, but I need both for an ethical compiler. Okay, so that's on expression. How do we express our ethical axioms? But once we have them, if we're working with a compiler, we need to preserve them. This is where most of my work has been. We need to preserve intent because no program is an island. Even after compilation, your program will not be finished. It will have to be linked against something. It will interact with the runtime system or the operating system or some other API, right? Some other code that could violate your values, could violate your ethical axioms, right? So in an open world, it is not enough to just express them, verify them once, get rid of them. Because once an ethical axiom is erased, it will eventually be violated. My favorite little example of this comes from Rock, where it's quite easy to make a verified program jump to an arbitrary place in memory. Doesn't really matter what this code does, but up here we have this declaration that this function ought never receive an empty vector. But of course, once I extract to a camel, all the types are erased. It's quite easy to call it with an empty vector, and we suddenly jump to the unit value as if it's a function. So my expressed intent that this function never receives an empty vector is not preserved into a camel in any way, not statically and not dynamically. And so my ethical axiom gets violated. So this is why we need to preserve intent. What ought to have been still ought to be after compilation. So how do we do that? Well, I find that preserving intent is much harder than preserving truth. And I'm not totally sure whether this is a universal statement or just the state of affairs in compilation. The literature is largely focused on correctness. We have lots of recipes for what compiler correctness is, how to prove it, etc., but not so much on what preserving intent, what ethical compilation is. And this leaves us with a lot of blind spots in various ways. There's lots of things where we assume this is correct. There are assumptions built into this about what it means, but it's actually unethical. And I have some more examples in the paper, and I'll walk through some. But I find that there is a productive recipe for doing ethical compilation, which in the same way that types express intent, type preservation can express ethical compilation. So type preservation says, I have a program E of type A. After compilation, I also compile the type compiled E should now have compiled type A. And this can express that my intent is preserved if we're careful about what type preservation means. It's quite easy for this to be a trivial statement, right? If I just compile everything to the unit value, it's type preserving, but surely my intent is not preserved. So this is actually an open research question. Lots of people working on type preservation. We've had discussions about this, and I don't know in general what meta theory we need to prove about type preservation so that it corresponds to ethical compilation. There's something about like the underlying expressivity of the types that needs to be preserved, but I don't know what that means. So if you have answers for me, tell me. Now, this is a great recipe, but unfortunately, in general, type systems rely a lot on syntactic structure, particularly as they get more expressive. And unfortunately, compilers change syntactic structure. So one of the key problems in type preservation is target languages can rely less on that syntactic structure. So it's harder and harder to design type systems for the IR, for the target language. And I'll give you a concrete example of what that means and how thinking about this in ethical terms has helped me. So consider a purely functional programming language, like SDLC. Actually, this problem comes from working on Coq, but we'll just simplify it to SDLC. In such a language, you get termination guarantees. Anything that is well-typed is guaranteed to terminate. But after compilation, you do closure conversion, you heap allocate all your data. Suddenly, you can tie Landon's knot. You can express backpatching recursion through the heap. So the compiler is correct. It's type preserving. But if I value termination, if I believe that my well-typed programs ought to terminate, suddenly my compiler is unethical. So how do I resolve this problem? So here's what such a compiler looks like. I have a lambda term. It has a free variable y, free within its own scope. I compile it down to a closure. Now I have lambda is closed, and it passes its environment around explicitly. So I project y out, and I package that up with y. Then I compile it down further. I malloc this. I stick y in one cell. I stick the function pointer in the other. That's my closure. Now, so far, all of this it's well known that this is correct in type preserving, but we have an interesting property here. In the source language, y can never refer to the lambda that it is bound in. This is just kind of a structural property that's easy to see. You cannot have a self-reference here without adding something. And that remains true after closure conversion. This environment cannot be accessing the same function that it's underlying. But once we're in a language with higher order references, as is well known, we can suddenly use the heap to smuggle the function pointer into itself, right? So I can update C0, which previously contained y, to now contain the function pointer and access it. And now I can get arbitrary recursion. This is quite unfortunate. The key question that I keep asking when I run into these problems is not like one of correctness, but it's one of ought. What ought to be true of this program? It was true that it terminates, and I do want that to be true, but there must have been something else, something more fundamental than that value that was true of the program that I was trying to express. So how do I, what ought to be true, and how do I express that in my type system? And I find viewing the problem this way has helped me a lot. So in this case, we keep staring at it, and what we see is, well, what ought to be true is that no computation, these lambdas, can have a cyclic dependency. That's true in the source language, unless we add fix, which explicitly adds a cyclic dependency. But it's not true in the target language, where we have a heap, an arbitrary heap, that can have cyclic dependencies. So what we find is, well, if we add basically a region system, where you can only have backwards references through the heap and not cyclic ones, it's very easy to have higher order references that are terminating. So we want a type system that expresses there ought be no cycles through the heap, and then we can preserve, by preserving typing, we preserve acyclicity and therefore preserve termination. So that's what we did in this work. And we kind of shifted our focus. We're not actually interested in purely functional programs. We're not actually interested in terminating programs. Well, the value we actually had was acyclic dependencies in computation. And that immediately eliminated Landon's knot, which added a cycle. And now we can preserve it. Okay, so focusing on these oughts rather than on any correctness theorem or even type preservation per se has been quite useful to me. Once we've preserved our intent, once we've expressed our intent, probably the most impactful area of work in ethical compilation is reconciling truth versus intent. This is the area I've done the least amount of work on, but actually I have the strongest opinions on. So let's see what reconciliation looks like. Again, with type systems, it's quite easy to see what we mean. E is true, like E is of type A, and maybe the programmer somewhere has expressed, yes, E ought to be of type A. And the type checker goes and it says, oh, great, your program behaves as it ought. Right? On the other hand, I might say E ought to have type A, And the type checker says, but E does not have type A. Something is wrong. This program is not in keeping with your values, and that's great too. But there's a very common problem. It happens in type systems. It happens in a lot of security work. Happens all over the place. I think we saw some examples of this earlier. Some person will come along and say, well, this is a lot to write. Why do I need to write this down if it's true? Surely I can just infer from what is true what ought to be. And that would be much better, much more pragmatic. Right, I'll add this inference. Now I know, well, because this is true, it ought to have been the case, right? But hopefully by now, with your ethics hat on, you know, wait, no, ought cannot follow from is. We cannot simply infer ought from is. So this use of inference is unethical. This is my fifth dictum. One should never infer ought from is. And this is just the application of Hume's is-ought gap to inference. Now, I'm not totally against inference. Inference is very tempting, very pragmatic, but it's also very easily unethical unless we keep it in is space. Inference can only tell you true things. It cannot tell you what ought to be. And that means if we're going to use inference, we should have the ability to express what inference is trying to infer. That doesn't mean annotations are mandatory. It means if I have no opinion, fine, infer it. But if I do value something, it must be possible for me to express that value and reconcile it against what inference is doing. So let me give you an example first of unethical inference. Again, from my favorite programming language to pick on, this is Rock. Rock's universe system. So Rock is a dependently typed language. Types themselves need types. That's what these annotated types are. This is the type of types. And in fact, there's not just one of them. There's like infinitely many of them. There's a bunch of constraints between them. Rock used to use a system called typical ambiguity, where you wrote down type, and underneath an inference algorithm will infer the level, infer a bunch of constraints between them, and make sure that this all works out. It doesn't really matter how that works. But the point is these highlighted terms have a bunch of hidden constraints that are inferred. And in this program, if you try to type check it, it says the following. Oh, actually, it doesn't type check. I expected this to have type blah, 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 which you never wrote down and have no values and no expectations about. But that's inconsistent with type other blah, 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 blah that you don't know anything about. So two things happen. I am not able to express where my type ought to live in this system. And as a result, I get very mysterious error messages about things I don't care about, that I don't value, that I have no expectations about. Yet the error message is telling me that I do have expectations. Right? So if I'm just totally relying on inference, this is quite unethical. There's no way for me to express what ought to be true. Thankfully, in recent versions of Rock, although I think for reasons entirely unrelated, they have addressed this problem in exactly the way I've suggested. They add the ability to add annotations manually. So I can say, I is a universe. I can add my annotation saying, oh, I expect all of these to be in the same universe. And then the inference algorithm will run and say, oh, but that's not true. These cannot have the same universe. The error message can still use some work, but basically what it tells me is actually one of these has to be greater than the others. So I add a second universe level here, and now it's very clear, oh, J actually has to be greater than I. And so trying to use I and J in the same way, which this program doesn't work. Right? So this is ethical inference. I can actually declare what I expect the inference algorithm runs, and I get an error that makes some amount of sense in terms of what I've written. So we have our ought space, our declarations. We have inference only running in is space, and then we have reconciliation where they don't match. Right? Now, the error messages in Rock are kind of terrible there, and there's a reason for that, and I want to look at a different example to show why. When you're doing reconciliation, you want to make sure you're reconciling is against ought. This case study comes from Will Crichton and his collaborators. It was on a grounded conceptual model of ownership types in Rust. And what they're looking at is Rust learners. So these are people who are new to Rust, trying to learn Rust, and are having trouble with the error messages. And what they're looking at is Rust programs. So in Rust, you declare some types, and the program, from the control flow and from the types, infers the ownership of various pointers. And from that ownership information, it also infers a bunch of permissions on pointers, which it then checks, and then it reports errors in terms of the types that you wrote down, which sort of makes sense. The Rust learners, they can express what the types ought to be, but they have no expectations about the expressions. They cannot express what the permissions on these pointers ought to be. And this results in quite mysterious, hard to debug errors. So here's an example from the paper. We have essentially the same program, just using slightly different types. The first one creates a vector, adds a bunch of integers to the vectors, project out a pointer into the vector, and then dereferences that pointer. The other one creates a vector, puts a string in it, projects out a pointer into the vector, and then reads from that pointer. One of these has a bug in it. Does anybody know what the bug is? Simple 3-line program, all the types declared. Yes?
Is string not copyable?
Oh, yes, string is not copyable. Excellent. That's exactly what the error message says. Cannot move out of sref because it's behind a shared reference, because sref has type string and string is not copyable. This is slightly a mysterious error message, particularly for Rust learners, because they didn't write anything about copy. They don't value copy in any way. It's not clear what move means here, because they didn't try to move something, they tried to read a pointer. So what Crichton et al. Argue is that the underlying problem is that what the programmer expects, like what they value, is memory safety, and they expect to be able to read this pointer. But the error message doesn't talk about that. So they developed some debugging information. It's much more graphically presented, but I've turned it into an error message that looks a little more like this. Expected read permission on sref, but string doesn't have read permission. If it did, then you ought to be able to drop it, but you can't because of memory safety. And the difference here is the difference of is versus ought. So in the first error message, we get a collection of inconsistencies, a bunch of facts. Cannot move is a statement. Move occurs is true. Right? String does not implement copy. But this set of inconsistencies doesn't communicate to what the programmer values. And in the second version, we try to express what the programmer values, what they expect, and how that is inconsistent with what is true, right? So this is trying to express is versus ought. So we expected a read permission because you actually tried to read from a pointer. It's kind of reasonable to expect you value reading from it. But string does not have read permissions on a shared pointer. If it did, you ought to be able to drop it, right? Because if you have read permission, drop takes a read permission and consumes it and drops it. But if you did this, there's a way to get a double free error here. And since as a Rust programmer, we assume you value memory safety, you cannot do that. And Crichton et al. Show once you present the debugging information in this way, where you're constantly doing this expected versus is true, you get much better learning outcomes. So that's my final meta-ethical dictum, that we should always be reconciling is against ought, particularly when reporting errors in terms of the programmer's expressed ethical axioms and values. Otherwise, you just end up reporting a bunch of inconsistent facts. Okay. That's my last dictum and my last example. Compilers shouldn't be correct. They should be ethical. Ethical compilation has 3 areas of research: ethical expression, expressing truth versus intent, preserving intent, and reconciling truth versus intent. We derived from these spaces in our initial question 6 meta-ethical dictums: that compilers should be ethical, that the programmer should be able to say whether something that is ought to be, anything that ought to be must be actually possible. What ought to have been should be preserved, it still ought to be. One should never infer ought from is, and we should always reconcile is against ought. I've written all of this down with more examples in the paper. I will now take questions. Thank you very much.
Okay, thank you very much for the interesting talk, and I guess there are a lot of questions. So, first, maybe.
So, I don't know how to phrase the question concisely, but I'll try to do my best. So, if you look at formal proofs, cock proofs of programs, many people claim, including myself, that the value is not so much or not only in the proof itself, but in surfacing explicitly the assumptions. Because many security attacks, for example, do not occur because the program is bad, but because you can see things that you're assuming you cannot see. Timing attacks, or timing leaks, side channels, and so on and so forth. So there is a role on the assumptions when we reason about correctness. And I presume there should be a similar role of assumptions when we reason about ethics. Right?
Yes.
So maybe your compiler is ethical under some assumptions, but is unethical under some others. Because when it's compiling, it's leaking information just because I have a much better observation as an attacker. So what's your insight on this explicit assumption claim?
No, I totally agree. So the question is basically, in correctness proofs, there's a lot done on surfacing assumptions that are sort of latent in some model when you prove a correctness theorem? And is the same true of a system of ethics? Is something ethical with respect only to, say, one person's system of ethics? And yes, I agree. So actually, what I've been talking about is kind of like a meta-ethically correct compiler or something, where yes, you have to be able to fix, when you say something is ethical, it is with respect to those ethical axioms, right? And that person's system of ethics. And so that's why when we rephrased this, we said it is morally obliged by someone's system of ethics, right? This is always relative to someone and their expressed values. So, and I talk about this more in the paper, it's not enough to have one set of values encoded in your language or in your compiler, right? And that's kind of the current state of the art. If you look at C, there's one set of values, more or less, which is performance, really high performance. And that's why security folks struggle with C, because they have no way of saying, well, yes, I want performance, but I have other values. And what we need is not just you encode one system of ethics, but that you have a system that lets you express many ethical axioms and values, right? This is one of the reasons I like type systems, because if a type system is sufficiently expressive, you can encode quite a lot of information, right? That's particularly why I like dependent types, right? I should be able to express things like what Satnam was doing. I value both correctness and really high performance in this dependently typed Haskell DSL, right? I want to be able to express both of those things. And one of the things I talk about more in the paper is that it's not enough to once and for all fix your system of ethical expression. We need something that is open to, when we discover new values, adding new ethical axioms that we can express. So yes, I don't think there will ever be one like definitely ethical compiler. It will be ethical with respect to the limited ethical axioms that can be expressed for its language. But I think right now, even that doesn't really exist.
So kind of as a follow-up question to that then, so you mentioned earlier that it's really important to preserve intent between the source and target language. Does this mean that you think it's inherently, or like impossible to write an ethical compiler where the target language is less expressive than the source?
Okay, so the question is it possible to write an ethical compiler where the target is less expressive than the source? I think yes, but it depends what you mean by expressive. So I talked a lot about type preserving compilation. So expressive here might mean I'm compiling from an expressive type system to an expressive type system. But that's not necessary. You could do an ethical compiler, in principle, that goes from a typed to an untyped language if in the process you instrument, say, dynamic checks, right? That's one way to preserve the intent. That will cost performance, so there are probably situations where you don't want to do that. But if in general the language of expression is, say, less expressive on all axes, like you're trying to compile a Turing complete language to an in-Turing complete language, I don't know if that's even possible, never mind ethical. Does that answer your question? Okay.
Thanks for the talk. It's really interesting. I was wondering, so there was a couple of examples that you've had. One was the paper where they added secure annotations to C, and then there was also the discussion of Rust.
Yes.
And what it got me thinking about was the interaction between defaults and ethics, in that in one of these examples, it was the being able to add secure explicitly after the fact, whereas in Rust, the default, it seems to be one of the strengths of Rust is that we're going to put you in a box, but you have an unsafe mode that you can go into. So the default is memory safe, but there is it's possible to write memory unsafe code in order to achieve performance or be able to write the libraries. And I'm wondering how does this idea of what default behavior, or where do you have to do more work in order to do something interact with simply ought or ought not?
Right. Okay, so the question is essentially about the interaction between ethical expression and what the default behavior of a programming language or a compiler are. So for example, in C, the default behavior is basically high performance. And you can slowly disable performance in C, but it's actually quite difficult to enable security at all, right? Assuming secure hasn't been added. In Rust, on the other hand, you get security by default, and you can escape into insecure land for performance reasons or whatever. I think they're always probably performance reasons. So I'm not sure ethics has much to say on this topic. I think this gets into, say, psychology or human computing interaction. Like how do you interact with a system by default is a very interesting question. And psychology researchers find like most people never change defaults. They will just accept whatever the default is. And I think it's a different question than ethical expression. In Rust, you can say I need to escape the confines of the type system and drop into unsafe, right? In C, at least if they haven't made these changes, you cannot say, I'm escaping into secure C, right? I'm enabling security and escaping the confines of performance. So I would say that Rust is more ethical because you can do both, even though one is by default. And in C, you can't do both, really. You just get performance. It's not, like, performance is not the default. It is the only thing you can do. Does that make sense? Okay, so I think, like, there's an interesting question about defaults, but the important point for me is you need the ability to express both.
Okay, sorry, I see many more questions, but unfortunately run out of time. But of course, we can move the discussion then maybe to the lunch break. So
okay,
thanks
I
again.
will hang out if people want to ask me more questions.
Okay, thanks again, William.
Thank you.
I can do this by my own. So no problem. As long as it's not difficult. If the other guy is here for the technique, so no problem.
Yes, thank you very much. Stand up.
Okay, so come to the next talk. It's about an algebraic stepper for simple modules, and Kenichi will present it.
Okay, I'm Kenichi Asai, and this is a joint work with my former master's student, Hinano Akiyama. Okay, so this is the algebraic stepper for simple modules. So what is the algebraic stepper? It's a tool to show all the intermediate steps of program execution. So in the elementary school, we have learned the calculation as reducing some expression to its result, and then continuing in that to the final result. The algebraic stepper is the equivalent for the programming language. So here is the stepper for Racket, and now in the Racket stepper, you can see the program, and by clicking forward or backward, and you can go, you can see how the program is executed and going back and forward and backward. And if you use that, then say we define a factorial of 5, a factorial function, then you can see that factorial 5 is expanded to 5 times factorial 4, and then 5 times 4 times, and you can see how the recursion is unfolded. And also, when we learned the the lambda calculus, then its semantics is given by small step semantics, and that is very close to what the stepper does. Okay, and when I first saw the Racket stepper, oh, this is great, I thought, and I need this for my OCaml course, and I implemented the stepper for OCaml, and I use it daily in functional programming course in my university. And it supports most of the basic constructs, so recursion, recalls, list, exception, and those things. But the one thing that was not supported was the modules. So this is the target of this talk. And there is a demo page for the OCaml stepper, and I also provide the, an environment for Emacs, and VS Code support is in progress. Okay, so but you might say that, okay, stepper is just a small step semantics. So a module is like a record. So if you have a small step semantics for record, why do we need steppers? And the answer is that, well, the stepper and small step semantics are not exactly equal. And this is caused by delayed substitution of variables. And in a stepper, a variable is substituted to its value using one step when it is used. So for example, we have that program. We first define a to be 10, and the function f uses that a. And after that, we want to step execute f of 100. And what we want to see is that f of 100 is expanded to a plus 100 rather than 10 plus 100. And then we want to see that a is expanded to 10 using one step. And in the small step semantics, this is not the case. in the small step semantics, if you define A to be 10, then that A is substituted in the rest of the program. And so the F now becomes 10 plus X rather than A plus X. And then F is expanded to in the remaining program. So what the user will see is not F applied to 100, but some functional value applied to 100. And this is certainly not what we want to see, but the novice programmer would expect to see the step execution in the middle. So the step semantics is not equal to small step semantics. And the other thing that is specific to steppers is that we want a variable to be replaced with its value in one step, but for the function, we do not expect that. So if we want to step execute f of 100 to a plus 100, but what is really actually happening is that f is actually evaluated to some functional value, and that is applied to the argument 100. But because the novice programmer would not know that f is a functional value, and well, they do not know about first-class functions, so they will see that f of 100 to be a function f is applied to 100, rather than f is first evaluated to some functional value and then evaluated. So in the stepper, we want that the variable having constant, we want to handle them as a regex, so that variable is executed to its value using one step, while a variable having a functional value, that is already a value, and it is expanded only when it is applied to an argument. Okay. And to accommodate these kind of behaviors, I annotate all the variables with its levels and values. And I will talk about levels shortly, so I will concentrate on values right now. So whenever we define first a to be 10, then we propagate that information in the rest of the program. So when we define a to be 10, then the a in the rest of the program is annotated with its value 10. And when we define f, then we annotate that value of f. We annotate all the occurrence of f afterwards with its value, functional value, and with these values we do step execution. So when we evaluate f of 100, because f is annotated with its value, we can expand it to its body, and then a is also annotated with 10, so a is evaluated to 10. And so on and so on. And by the way, these attributes, these annotated values are for internal implementation only, and the user will not see that. So users will see the step execution to the left. And this appears to be quite natural, but there is one design choice here. So if we employ delayed substitution of variables, it means it allows apparent name clashes. So suppose that we define A and we define F as before, and then we redefine A to be something else. And that does not affect to the value of A. But if we expand the F of 100 at the bottom with A plus 100, seemingly that A is captured by the second definition of A. And in the stepper, this does not happen because all the values are annotated to its variables. So A has the correct value 10. But apparently, if we see the A plus 100 only, then it appears to be captured by the wrong one. And in the OCaml stepper, I chose to allow this kind of interaction because most of the time, people do not redefine functions in this way. And the standard way to avoid this problem is to rename the second A to something else. But it means that we have to rename A and all the occurrence of A in the rest of the program. And that is not very nice to novice programmers, I thought. So this is the current design. Okay, so far so good. So what if we introduce modules? The program, OCaml program, it consists of a tree of static modules, and modules can contain a variable declaration, type declaration, and another module declaration. So you can form the list of static modules. And they are evaluated once in the order of appearance. And here is something that we have to note, is that variable reference. Well, you can refer to a variable that is declared outside the current module without any module path. But if you want to access a variable within a module, you need a module path. So from within the module X, you can refer the X that is defined outside the module. But from the outside module, if you want to refer to the G in the module X, you have to say X.G. And this kind of things becomes problem because of the delayed substitution of variables. So with the delayed substitution of variables, we need to write a variable reference, and that variable reference has to have the right module path. So we have to keep track of that. Okay, so let's see what happens with this program with modules. So whenever we define a variable, then its value is annotated in the rest of the program. So if we define A to be 10, that information is propagated to the rest of the program. But when we see another A is defined, then the substitution stops there. That A shadows the original definition. So the A in G is not annotated with 10. Okay, and we go on to the F. So F, when we define F, its value is propagated to the rest of the program. So in the F in the third line, it is annotated with that value. And within the module, the F is also annotated its value, but its level is increased by 1. So that level designates where that variable is declared. So level 0 means that variable is declared within this current module, while the level 1 means that F is declared one level outside the current module. So that is the kind of Brown index. So whenever you go into the module, the levels increase by 1. So F is now declared one module outside the current module. And also A is also declared in the module outside the current module. So A gets the level 1. Okay, and then now we go on to the A in the module X. And that A, the information of A is also propagated into the rest of the program within this module. And that second A in the function G now gets the value 20. But the one in the F is not annotated with 20 because that one refers to the original A declared at line 1. So variables in the attributes are not affected by this propagation of values. Okay, and then the G, the value of G is propagated to the rest of the program, and then the step execution goes as expected because all the variables has its value in its annotated values. Okay, so far so good. And then what happens if we have finished evaluating a module X, and then we use it in the rest of the program. So when a module is fully evaluated, its information is also propagated to the rest of the program. And so at this point, we use X.G, so we use G in module X. So the value of G is propagated there. And here, the interesting thing happens, and when we propagate a value within a module to the variable outside the module, the levels are decreased by 1. So in the final line, f gets the level 0 because f is now declared in the current module because we get out of the module x. X is now declared in the current module. So the level of f changes from 1 to 0. And it's the same for the f in A. Sorry, A in F. A had the level 1, but now we are out of module X, so A now gets the level 0. And interesting thing happens when the level is already 0, which means that we get out of the current the scope where that variable was declared. So now we need the module path. So at the last line, the A gets the module path x dot because A had already indexed 0. So when levels are already 0, module path is attached. And this is it. And so with this in mind, you can write steppers. And that's almost all. And later on, from now on, I will show some formalization. But, well, that's kind of straightforward. OK, so here's formalization. I will show that the stepper semantics and small step semantics both in this slide, in the following slides. And so this is a simply typed lambda calculus with modules. And in OCaml terminology, OCaml program consists of a structure, and structure is a list of structure items. And structure items is one of let declaration, variable declaration, or module declarations. And to that, we add the variable with annotations. And the first one, PG annotated with function, that is a variable annotated with a function. And a variable with a function, that is a value. That is a value, while annotated, sorry, variable with a constant, that is an expression because that will be evaluated to its value using one step. And here are the reduction rules, and we have a standard beta reduction, and on top of that, we have a reduction rule for the annotated variables. So a variable with a constant is evaluated using one step to C, and that is the reason why A plus 100 is reduced to 10 plus 100 using one step. While variable with a function value, that is not a value, but that is reduced only when it is applied with this argument v. And this, because of this rule, f of 100 gets a plus 100 rather than f evaluated to its function value. And here the evaluation rules for modules. And whenever we want to reduce a module, we first search for the unevaluated structure items. And when we get the let expression, then we will evaluate its body. And when all the things are fully evaluated, one of two rules are used. So when we see let x equals v, then we propagate that x now gets v. So we propagate that information to the rest of the program. In the standard semantics, small step semantics, all the occurrence of x is replaced with its value v, while in the stepper semantics, we replace x with the x annotated with v. And that's the same for the structure declaration. When all the structures, ingredients of the structure are fully evaluated, its information is propagated to the rest of the program. I will not go into the substitution of structures, but that's straightforward. You can do that. And well, with that, I can show some properties. So define the erasure E of by replacing all the annotated variables with their values. So we strip off all the variable part and replace that variable with its value. Then we can show the correspondence between small step semantics and stepper semantics. So whenever in the stepper semantics E1 reduces to E2, then its erasure reduces from E1 to E2 in the standard semantics. Because of the delayed substitution of variables, delayed substitution of variables, you might fear that the order of evaluation might change, but this theorem says that it does not happen. There is a one-to-one correspondence between stepper semantics and standard semantics. And one thing to notice that because this erasure erases the variable and replaces it to its value, so it throws away the variable names. So it does not, it says nothing about if the variable with the module path, the name I gave to the stepper, that is correct. So this does not guarantee that the names are correct or not. So we have already seen that in some time we have name clashes. So that stepper semantics cannot be correct in that sense. So this theorem says nothing about the correctness of the names. Okay. Well, in 2001, Clements designed the scheme stepper, and that was great. And after that, we have been working on OCaml stepper for quite a long time. And and there is one work by Whittington and Rich who showed an OCaml interpreter that supports tracing all the intermediate results. And one particular point of their work is that they can import standard libraries in their steppers, in their stepping interpretation. So they can use list module or other modules. However, it seems how they handle modules is not clear from their paper. And when I tried my program that I showed you today, with their implementation, it failed. So it was rather sad, and I want to see how they are handling that, handling module references, but I did not quite see what was happening there. And there are a bunch of work on modules, and those work on modules are mostly for advanced features such as functors, recursive modules, first-class modules, and they are mostly interested in typing aspects. And only a few of them talks about dynamic semantics. Well, dynamic semantics is only about the record calculus, so it's not very sophisticated. So they are not talking about small dynamic semantics very much. And one express section would be queries work, where he implemented the small step semantics in Coq. So, but of course, he is implementing the small step semantics, and that is not the same as stepper semantics. Okay, so current status. I implemented the OCaml stepper for the version before 5, and it's used in my university in a functional language course. And maybe the take-up out message would be that stepper semantics is not equal to small step semantics because of the delayed substitution of variables. And maybe it's nice if I could support the algebraic effects of OCaml 5. That is something I want to do. Maybe I could incorporate functors, but I'm not quite sure. And one of the motivation for using module is to support abstract data types by hiding the implementation of modules. But the signature sealing and stepper appear does not appear to live well together, because if we hide the implementation, what steps do we want to see? So in the current OCaml stepper implementation, we just ignore the signature sealing and expose all the internal structure. But if that is good or not, I'm not quite sure. So if you have any ideas on that, I'm happy to hear that. Okay, thank you very much.
Yeah, so thank you very much for your presentation. So questions?
Thanks for a nice talk. I couldn't help wondering whether your system is ethical or not. My initial thought is it probably is ethical if you're a sort of beginner programmer doing some simple examples, but if you start having examples where you do have shadowing,
Yes.
then I can imagine getting really confused, and particularly with modules. And then at that point, perhaps you want to, I don't know, have some sort of knob that you can dial to allow you to see more information. And I wonder if you've thought about how to configure the system so that you could see a bit more information. And this certainly is going to become more of an issue if you add things like functors and you already.
Yes. It depends on who wants to use this tool. And this is for the very beginning students. And right now, I rather not to rename or doing that kind of things. But maybe, yes, we could add a note that could, yeah. So, and if this is ethical, well, so we have to study what is ethical for beginning students, I would think.
Maybe first, or maybe directly.
Well, I'm not going to talk about ethics, actually. We can do that later. No, my question was, so particularly, so I appreciate the paying attention to how binding gets manipulated during evaluation. And I was thinking a lot about Racket's set of scopes implementation recently in their macro system. And I was wondering if you could comment on, so if you don't know anything about the set of scopes, this is how the Racket macro system manages binding when it's being manipulated during compile time. And it's very hard to debug. And I was wondering, this stepping looked a lot to me like some of the stuff that goes on in set of scopes. And I'm wondering if you know anything about that or have looked at the connection or could comment on it.
No, I've never done any work on that. Macro system, yes. That's very hard for me too. And yes, I could think of that. Yeah. Thank you.
Okay, so
I was wondering if you could say more about how you've seen students, learn before this tool was there versus after. Have you seen, any experience with the students?
It's very hard to say because, well, there is one paper that shows some light on that. So there is a check system in my course, and students, whenever students complete their work, they submit their program to the check system and see if it passes or not. And the time from the start of the exercise to the time when they finished it, it appears that that time is shortened after introducing the stepper. But because this kind of educational work is very hard to actually validate that thing, so I'm not quite sure if that is really because of the stepper, but I have one paper describing something.
All right. So you're explicitly not showing the evaluation of functions to closures, but so I'm tutoring a introduction to programming course also at our university in Kaiserslautern, and there actually my supervisor Ralf Hinze has made the very specific choice to show people, to actually show that the semantics of an expression is that it gets reduced to a closure, to make students more comfortable with functions as sort of first-class values. Yeah. So here again, sort of an ethical question. You want to hide the fact that functions also have a semantics of becoming closures to not confuse the students, but then what may the effect be? Maybe this leads to a delay in kind of accepting functions as first-class citizens.
Well, I have no data about that. right now I'm using this, but in the later course, I also, of course, I also introduce map and faster class functions, and right now I don't have any problems when we enter that part. So I hope that it's fine, but maybe we could introduce a switch to see if it's evaluated to value or not. Yeah, that could be one possibility.
Okay, so thank you very much. We saw more questions, but we have to stop here. So, and now we can switch to the last presentation, which is a shorter presentation, short paper.
Last one before lunch. Hello. Okay, so there we go.
Okay,
There's
so
my
you
mouse.
already see the title about collapsing towers for site channel security.
Sorry, let me
And
pull up my notes.
Cameron will present the paper.
Yep.
So-
Yeah, so thanks. So this is a small part of a much larger project with everyone on the slide you can see right now. So the bumper sticker for the next 10 minutes, however long, is we want to use staging to detect side channels. And when I say side channels, I specifically mean timing side channels. There's all sorts of side channels, but we're only worried about timing. And specifically, even more specifically, we care about microarchitectural side channels. So for those of us who haven't spent the past however long thinking about how horrible computers are, here's an example of what's called a Spectre vulnerability. So just to kind of elucidate the problem statement a little bit more, we're going to have some kind of secret value in memory. This could be some kind of password and encryption key. For the sake of this example, it's just a secret number. And we have a user who gets to interact with the program at this very clearly defined point. And we want to make sure that the user can't learn anything about the secret. So just looking at this is really easy, right? The word secret doesn't appear anywhere in this program. How could it possibly leak anything? Now, since I opened by talking about side channels and microarchitectural side channels, the first thing you might notice is, okay, this secret value, depending on how the compiler might lay it out, this secret value could come right after this public array in memory. Which means that if we can get the program to read from pub sub 8, then we could be in trouble, right? We've influenced the behavior of the program by reading from this secret value. But that's not to worry. We have this if condition right here that guards against this out-of-bounds read. But thanks to the magic of branch prediction, where hardware might decide that actually I don't have to check this branch prediction just yet, we could initiate this memory load before we realize that we shouldn't. So we're going to go under the shadow of this if condition, start reading the memory load, and then we decide, oops, actually we shouldn't have done that. And this is going to affect the hardware cache, right? We're going to load this pub sub secret into memory, which means that if the user guesses what the secret is and they decide to input that, then that's a cache hit. And if they can clear the cache and run this over and over again with a bunch of different guesses, then one of those runs is mysteriously going to be faster because one of them is going to have a cache hit and the rest of them are all going to be cache misses, which means they've now learned the secret. So how do we catch this? The really scary thing about this vulnerability is that this relies on a particular combination of hardware components, right? If we just look at the surface language, we actually did guard against the out-of-bound read. So this is not only an out-of-bounds read, this is a phantom out-of-bound reads. Particularly, this manifests from the fact that a phantom load will affect the cache, and this effect does not get unwound when we find out that we shouldn't have gone under this branch. So the classic way that we solve this is we're going to design some kind of cost model that we know about caches now. We know about speculation now. We have some really fancy analysis. And there's a lot of work on that. I'm not going to get into it. That's not really the topic of this talk because we're going to do something different. What we want to do is we're going to say, here's an input program. I want to do some pre-processing on this input program such that I have some intermediate representation that includes all of these hardware effects. We're going to write them into the thing that we're analyzing. So what I mean by that, well, if we go back to this example, the key thing that went wrong was that this read here side effected some global state. Particularly, it loaded something into the cache. So why don't we just insert some code that tracks the cache? So how are we going to do that? How are we actually going to do this transformation? Well, the answer is staging. So I'm going to shift gears and kind of talk about what we've actually been doing so far. The plan is we're going to start with a hardware interpreter. For the sake of today, we're going to take in some assembly program, some input, and we're going to produce the output of the program, and we're going to produce some number of ticks. I'm going to be intentionally vague about what constitutes a tick here. It could be interpreter cycles, it could be hardware cycles, whatever level of granularity you want, and you can include whatever hardware effects you want, speculation, caching, blah, blah, blah. Next, we're going to add some staging annotations. I'll explain what that means in a moment. And this is going to transform this interpreter that we started in into a compiler that takes in our service program and produces what we call a residue program. This residue program is then going to take in the true input of the program and then give us the same timer and output as before. So effectively, we've curried our interpreter and specialized it to the program we want to analyze. And the key thing here is that this residue program is just a standalone program, right? We have some intermediate representation, we spit it out, and this is now our artifact that we're doing our real analysis on. And the timer here is now just a first-class output, right? We're just going to have a program that spits out a number, which means that we can use any kind of non-timing aware, non-hardware aware classical analysis we want to enforce properties on this number. For example, that it's not influenced by any kind of secret. So as a more concrete example, here is some of the actual code from our proof of concept. We're going to, you can see we match this instruction. If it's an add, we're going to do an addition. Then we're going to add these rep to the type. So if you're not familiar with stage programming, and particularly staging with types like in Scala LMS here, what this rep means is that if we have a value of type rep sub t and we manipulate a rep sub t, we're adding nodes to some internal syntax tree instead of doing a real computation. And this return type of rep sub unit here means that we're going to return that syntax tree as the result of calling this function. That syntax tree then gets spits out. That's our residue function. Congratulations, we've now staged an interpreter. This is a quote unquote hardware compiler for some definition of compiler. So here in the bottom right is what the output of this particular case might be if we choose to exercise it. And you can see how the timer, this is just like a straightforward timer plus equal 1 that gets reflected into the resume, as well as this addition that also shows up. But this instruction dispatch, where we actually check what kind of instruction we're looking at, that's not there. We just emit a straightforward addition. So for the actual analysis then, this is the driver from our actual proof of concept. I'm not going to go over all the details of what's going on here, but this is basically, this is a regular assert that we're using with an off-the-shelf bounded model checker. Doesn't know anything about timing. We're just checking a regular struct value that happens to be named timer. And we're enforcing that between two different runs of two different secrets, the timer is the same. Now, at the beginning, I promised that we're going to do caching speculation. Then I just show you an example that's a timer plus equals 1. So how can we extend this to deal with caching? Well, on screen is this memory load case from some of our proof of concepts, and I want to highlight this getMem function. With the magic of object-oriented programming and overloading, we could just do the naive thing. We have some memory in our state struct, and we're just going to read it. Or we could write a cache simulator. This is, again, very straightforward, and you can see there we have this timer plus equals 100 saying that a cache miss is expensive. This, too, will get reflected into the residue normally, which means that, again, it's just a straightforward value that the bounded model checker is going to see, OK, that's a plus 100, that's bad. So we didn't do anything special, right? We just wrote another interpreter. I'm going to claim an interpreter is easier than writing a new analysis. If you disagree with me, well, I don't know. I'm not going to show speculation because it doesn't fit on the slide. It's kind of messy. It's in the paper if you want to see it because we have to hook into the interpreter loop, but it's not that much more difficult. Kind of works the same way. So concretely, what have we actually managed to do? We can detect timing leaks from all sorts of different vulnerabilities that involve different combinations of caching and speculation. We have one that's just a naive timing leak. We have one that only shows up with caching. We've detected the Spectre vulnerability I showed at the very beginning. Our infrastructure is also very modular. We can use all of your favorite software extensibility tricks to swap out components. So this is kind of our value add here. We didn't have to design a new analysis. All we did was we wrote a cache simulator and plugged it in. What have we not done? What are our future directions? So the big one is that we've written, so far, all of our hardware interpreters by hand. Real hardware is messy and complicated, and writing a staged interpreter, or even just a regular interpreter, for these is very messy, very complicated. So what we want to do is be able to generate a staged interpreter from some kind of HDL. I don't know. Pick your favorite HDL, Verilog, whatever. We want to do that. I also mentioned that we can use any kind of classical analysis on the residue. So far, we've kind of only used bounded model checking. We have some kind of experiments with taint analyzers, data flow analyzers, program slicers. So that's an exciting new direction that we're working on. And the biggest one is that we want to move more of the analysis into the stage interpreter itself. So far, we just wrote an interpreter and stuck some labels on it. But there's some exciting work about using this same technique to turn an abstract interpreter into an abstract compiler. And we want to kind of apply the same methodology to kind of transform the input to a way or to a form that's more amenable to analysis. You know, maybe there's some knowledge that we can know at runtime that we can reflect into the residue that makes the analysis easier. So what are the takeaways? Side channels are hard, in my opinion, because they require reasoning about a lot of different interactions between different components. We get some kind of n-squared problem. So instead of writing n-squared different models for all these different interactions, why don't we just have a system that allows us to expose the details to our existing analyses, right? No new analysis, we're just gonna lift everything to the surface where our existing analyses can seize them. Staging is a great way to do this. We have a bunch of levels, and staging is a great way to collapse them together so that everything's visible. And yeah, that's collapsing towers. Thank you so much.
Okay, thank you very much for the presentation, keeping the time limits. So, are there questions? So Seth.
So, your system makes it easy to detect when there are possible timing attacks. What about, have you thought about building a system that just rules them out statically?
So the question is, have we like tried fixing the things we detect? No, this is detection, not mitigation. So one of the big flaws in this technique is blame is very hard. If I have some surface program and I say there's a leak on this hardware, we have no idea whether the leak is the hardware's fault, the surface program's fault. Where would we even begin to fix this? This is something that we have on the horizon, but it's so far not really a goal.
So I have a question. So you have already mentioned it in future work. So how can you describe the different kind of leaks? But there has been some leaks detected in the last year, and how positive you are with your method that you can detect them, or also in the future.
I'm not sure I understand the question.
So if you look at the problems which have been detected with caching and so on, and sometimes they have been fixed, so it's on the practical side. So do you think you can, from the existing attacks, you can detect them?
So one of the end goals of the larger project here is for iteration of these systems. So if someone detects a new vulnerability with some specter mitigation technique and it turns out not to work. Right now, the way that you use formal methods to say, okay, we actually fixed the problem, is you sit down and someone thinks really hard and you spend a year writing a new model, and your formal method said, cool, we didn't find any errors, and then it turns out that the formal model's wrong. One of the goals here is that because we think that writing an interpreter is easier, we can iterate more on checking all these different combinations. So, if something's detected, it's relatively lightweight to just mod the interpreter to do something different and see, okay, does that make it go away? I don't know if that answers the question.
Yeah, okay. So there is one question.
Thank you for the talk. This is more about example of your work, like what's the application of your work? Do you have some concurrency example for your system, or it's just for the single-threaded program?
So the question is about concurrency. That's something that we're definitely looking towards. So far, single-threaded, we were already running into some tractability problems that we'd like to iron out before we even think about doing concurrency.
Okay. So, thank you very much for the presentation. And this closes the session.
I think I should wait some more. The people sitting down. Well, the first talk is keynote talk. I don't think I need to introduce Bridget, but she has been working on many things, and mainly for the mechanization of higher order languages and other things, and today we'll have the type theoretical form of work for meta programming, and I want to start, but maybe.
Okay, I think the mic is on, so while there's still a seat over there, yeah, if you want to squeeze in over there. All right, so what I want to talk to you about is this type theoretic framework for metaprogramming, and it's something I've been interested in for, I don't know, 15 years or something like that. And so some of the work I will be presenting was at LIX in 2019, but over the last year, I kind of understood that it's actually a framework for metaprogramming. It's not how we wrote the paper. Okay, so sometimes that happens with research. You learn something later on, how you can rethink some of the work you've done yourself. And so when we started this work, David Thibodeau and Francisco Ferreira, two of my PhD students, were involved in this, together with Andreas Abel. And then now we kind of, this work became sort of has new momentum after the pandemic. And so Antoine Goulin, Jason Hu, and Junyang Jiang, who's actually here, they're involved in this work nowadays. And Jason has by now graduated. So when we think, what I want to do is basically two things. Okay, I want to give you sort of a bit of a background and context in which this work sort of exists and where some of these ideas come from. And then in the second half, I'll explain a bit more how we can turn then these ideas into a type theory. And in the last part, I basically show you some of the new research directions we're performing. So when we think about metaprogramming, many people have different ideas about metaprogramming. Okay, so I think it's good to sort of, that we're all on the same page to define what I mean by metaprogramming. And I think of metaprogramming as a way of writing programs that produce other programs, essentially. Okay? But I don't want to only generate programs. I also want to then manipulate these other programs. So I want to pattern match on the structure of the code I have generated to maybe implement some kind of specific program optimizations or program transformations. Or in the context of a proof assistant, it's basically implementing a proof transformation, okay? Basically like a tactic. And I would like to do this in the same language, okay? So typically metaprogramming systems, and many, many systems support metaprogramming, they support at least 3 operations and sometimes 4. So the first one is a notion of quotation, where we can quote a piece of code, 3 plus 4, okay? I can think of this as an abstract syntax tree with 2 children, and that is the syntax that I will then manipulate and work with. The second operation is sort of a notion of splicing or code composition. So let's assume code gen of 2 generates this code fragment 2 times 2. And then I can say, well, 3 plus unbox this code fragment, code gen of 2. That will essentially give me this code 3 plus 2 times 2. And these 2 are different abstract syntax trees. Okay? And the third operation that I would like to support is evaluation. So at that point, we want to actually evaluate that piece of code using the runtime system or the evaluation semantics of the metaprogramming environment. And in this case, we do get 7. And the fourth operation that is not supported in all the metaprogramming systems, but it's something I would like to support, is essentially a form of code transformation. So I'd like to be able to implement a program that would inspect the shape of this arithmetic expression, possibly even having some free variables in them in this so it doesn't need to be only numbers, 3 and 4. It could be variables, replace 3 by x and 4 by y. Okay? And I might want to implement some kind of decision procedure for arithmetic. And I would like to simplify this by saying, well, this actually reduces to the left side of this sum expression. And you wouldn't get that necessarily if you have replaced 3 and 4 by variables, because the way we would normally define evaluation for times, it's recursively defined on the first argument, and plus is recursively defined also on the first argument. So in a dependently typed system, you wouldn't get that equation necessarily for free, but you might want to implement it as a actually transformation of your code. Now, I said metaprogramming is supported widely, and I'm sure many of you have used it. Okay, it goes back to ideas from Lisp and Scheme. We see it in languages like Scala. We see it in languages like template Haskell, MetaML. You see it in some things like Metacoq. Okay, Lean has metaprogramming. There's something like template Acta. Okay, so it is virtually in every system. And there are good reasons why. Okay, so on the one hand, if you're a programmer's perspective, you would like to implement maybe domain-specific optimizations. So Satnam talked about metaprogramming, for example, in the context of machine learning, where you have a matrix and a vector, and you want to multiply them. And you might want to actually analyze the shape of the matrix, and depending on the shape of the matrix, you might want to actually then generate a more efficient way of multiplying the elements of the matrix with your vector. In particular, if it's sparse, and you have an entry that is 0, you might not want to generate 0 times this element from the vector. You might want to just throw that away. There's also, certainly, it supports macros and boilerplate code. Okay? And in proof environments, there's this idea that we want to use reflection. So you basically quote a proof goal. You get the syntactic representation of your goal. You can write a transformation of that goal. Okay? So by, for example, calling a tactic or a decision procedure that will transform it into something else. And then you reflect it back to the actual proof assistant you're working with. But there's sort of something unsatisfying about this from my point of view. Okay, so first of all, I personally believe in types. Types are good. I think many of you believe types are good, hopefully. So because types allow us to weed out errors early on. They give us sort of a good safety net for the things we work with. Okay. But if we look at how metaprogramming is realized in languages like template Haskell or Metacoq or Lean, it is really you get an untyped representation of the code. Okay. So there's certainly work on typed template Haskell. But if you look in proof environments like Lean or Metacoq or template Acta, what you get is essentially a data type that's called TM, and it codes up all the terms in the calculus of construction or all the terms in Martin-Löf type theory. And then the first question is, how do I represent variables? Well, variables are just De Bruijn indices. They're not even well-scoped De Bruijn indices. Okay, so you can do all kinds of De Bruijn index manipulations, just the same way you can do pointer arithmetic. You can now do De Bruijn index manipulations. Okay, and we believe pointer arithmetic is bad, and I also believe managing your De Bruijn indices explicitly is also bad. Okay, so why do we not use something better? Okay. And in particular, why don't we use something that actually guarantees that the objects we're having are well-typed objects? Okay. And MetaML certainly took the lead on this, early around 2000, to actually support a form of typed code generation. Because if it is not typed, right, then it's really hard to test and reason about the code generation and the generated code itself. And you will catch errors not at the generation time, but essentially when you're using it or when you're running it or using it in some form. And the last point is also very close to my heart, and that is sort of more a philosophical objection I have to these systems. Because what happens in these systems here, like Metacoq or Lean, it's essentially clever engineers added to the system a way of quoting. And that's great. I have a lot of admiration for the people who did this. Okay. But what I would like to know is, what is the type theory we are now working with? Okay. It's certainly not Martin-Löf type theory. It's not the calculus of construction, because it's Martin-Löf type theory plus this quotation thing. Okay. And so what is it? Okay. So since I'm a theoretician, I'd like to understand what it is. And so really, I would like to understand what is the type theory behind quote, unquote, eval, and pattern matching on code. So what I want to tell you about, I want to take you on this journey, essentially, of developing these ideas that go into this type theoretic foundation for metaprogramming that would allow us to catch errors at the time we're generating code, We can also then reason about the code generation and the generated code because we're working in a type theory, okay? So we can prove properties about it. We want to have a support for code analysis, so pattern matching on code, so we can write our own tactics within this language. We'd like to have a proper logical foundation. And the last point is something I also think a lot about, because if you think about writing a decision procedure for propositional logic, okay, or for Pressburger arithmetic, that's not, you don't need to handle all of Martin-Löf type theory, right? It's a fragment of it. And in some sense, I know what fragment I want to handle, okay? I want to handle propositional logic, okay? I want to handle Pressburger arithmetic. So really what I would like to do, I would like to write meta-programs over sub-languages that you can carve out and then make statements about. So, so let's start at the beginning, okay? Because I don't make any assumptions that you know anything about type theory, okay? So where should one start, okay? And so, in fact, there was a very beautiful observation back around 2000 by Rowan Davis and Frank Fenning, who observed that the box modality from the modal logic S4, which is the necessity modality, can be used to describe closed pieces of code. Okay? And the reason is because if you say A is necessarily true, it is something that is really true in every world, okay? And that means in every stage, and so you can basically run it at every given stage of your program. And that gave you the separation between generating code, okay, which was essentially of some type B or C, and then the code that was being generated, that was essentially of type box A. But this work is only simple types, right? It doesn't have any pattern matching on code, okay? So that's still a long way from what I actually want. But there was certainly work in between, okay? So around 2008, for example, we extended this idea to the idea that we can describe open code, okay? So that means code of type A that has free variables in it, and these free variables are in gamma. And at POPL in 2008, in fact, I proposed a language that did support a form of pattern matching on these kinds of contextual objects, but it was mostly simple types, okay? And it was the basis of this programming environment, Beluga, that some of you might have heard of. And ultimately, this led to this paper in 2019, which is actually a Martin-Löf type theory that allows you to talk about open pieces of code and allows you to pattern match on these pieces of code. So we'll start slow, okay? We'll start from these ideas and we'll end up in these ideas, okay? So no worries. So what's the general idea? So let's look at some examples, okay? So there's no talk on metaprogramming that can live without the power function. So here we have a natural number and it generates code, namely a natural number that depends on this variable x. And if you have power of 0, then you return 1. Okay, it raises x to the power of 0, which is 1. And if you have power of n, you compute power of n minus 1. Okay, so that will compute already n minus 1 times x, okay, axes. And then you compose this code and multiply it by x. Okay. So if you have a power of 2, a power of 1 will generate 1 times x. Okay, and then you splice that in with this additional times x. Now, you might say, well, okay, but how do I know, okay, that power of 1 actually generated 1 times x, okay, and this is this x that I want to have and I'm generating power of 2, because in some sense it should, you know, the name shouldn't matter. If I use it x, y, or a or b, it should be the same. And so really I was lying a little bit here, okay. What we should have here is an unbox or a splice that will possibly rename the free variables in this open piece of code. Now, renaming is maybe not that interesting, but what is more interesting is if I actually refine the piece of code, okay, or specialize it. So here's a program where I want to get the nth element out of a vector or a list. I restricted it to natural numbers lists. And if you get the 0th element, it's the head of that array, of that vector, okay, or that list. And if you want to then compute the nth n element, okay, you compute nth of n minus 1, okay, and then you need to replace that list with the tail of that new list, okay. So you see that actually happening here. I mean, nth of 0 will compute the head of x, when I want to get the first element then, okay, I need to take the tail of the head, okay, and if I have nth of 2, I do head of tail of x, okay, I have 2 tails. So if I have here nth of 0, okay, I'm going to replace this x with tail of v, or tail of x, okay, so I get this tail thing in it. So I can specialize head of x to head of tail of x. Okay. So here we see that it's not just doing a renaming, it's actually doing a specialization of the code that we've generated prior. So what's the theory behind this? Okay, so there are typically sort of 2 different strands of theory that could support this form of a box modality. And I'm going to show you one that is really focused on this box-unbox idea, which is really grounded in sort of this, in this model theoretic view of modal logic, where you have this notion of Kripke worlds. Okay, now this is maybe a funky words you don't know much about, so that's okay, because we are only restricting this to 2 stages. Okay, so what I will do is I will take the original work by Rowan and Frank, restrict it to 2 stages, and I will make it more general by looking at how we can make it contextual. So if you, and for pedagogical purposes, I'm going to disentangle these 2 stages. Okay, so you have one stage which describes the code. In our case, simply type lambda calculus. Okay, so that's in blue, and it has variables, functions, applications, and we know exactly what types we have: natural numbers and functions. And then we have a level where we have programs, and that's where we extend, in some sense, our simply type lambda calculus with the ability to quote code. Okay, so here we quote code, quote that stands for a simply typed expression. And we have a way of describing the type of that piece of code. It's of type tau with a context gamma. And the splice, so which was previously written as unbox, okay, I wrote it here with these angle brackets. Essentially, here we splice in a program. We would evaluate this program to a piece of code, to a piece of syntax, and then the sigma is this width, okay, where we do some renaming or we replace the variable with a tail of some other variable, okay, so which basically gives us this refinement. And then we have here eval, which takes in a meta program, it evaluates it to some piece of code, and then we use this runtime, this environment row to actually run it. Okay. So you see that there's already a lot of overlap with the syntax, but really it's useful to sort of separate them, especially if you want to do pattern matching, because here I actually know exactly the shape of the code, right? If it's a fully evaluated piece of code, a full value, then it will be exactly describing the syntax of the simply typed lambda calculus. And essentially, you have 2 levels of typing. One that is the level for typing program expressions, and one is the level of typing for code that can refer to the local variables, which are in gamma 0. These are code variables. And gamma are still program variables that might be used because I'm referring to programs, right, by unboxing that variable or unboxing nth of n minus 1. N would be this kind of program variable. So what does this look like? Okay, well, everybody hopefully is in some way vaguely familiar with the simply typed lambda calculus. So this is the simply typed lambda calculus. Okay, everybody happy? Now this is also the simply typed lambda calculus. Okay. Except that I have 2 contexts. Okay, I have the context that says I have here the local variables that describe code, and these are my program variables that I could still access. And how do I access program variables? Well, I haven't shown you box and splice. So I access program variables because I can essentially refer to programs. Okay, so that brings me back to the previous world I was in. And that will denote a piece of code. And then I have here a map that moves me from gamma 1, which are the code variables in the code that I've generated. And I want to use this in a code context where I have gamma 0, so I need a substitution or a map from code variables to code variables.
My poor eyesight doesn't let me.
This is, sorry, I can't change that. So this is just says gamma and gamma 0. Okay, and this is referring to the turnstile, which is for the code typing This is sigma, which is a substitution, and this is gamma 1. Okay, so gamma 1 comes from here, gamma 0 comes from here, so it's a transition between gamma 1 to gamma 0. That's what it means. Okay. And in the introduction rule, it basically says when is a piece of code well typed? Well, we transition to type checking E as code. Okay. So we go back between these two layers. And for the elimination rule, which is actually logically on box 0, okay, it is this law that basically says if you have box A implies A, then we, again, evaluate E to a piece of code. And then this here is a transition between gamma 0 and these program variables. Okay? So this is a bit different because it means essentially you have code variables for which you plug in actual program variables, program values.
What's the hat on the gamma 0?
So the hat here is essentially saying it's only a list of variables without their typing annotations. Just the same way I don't have typing annotations on the functions, I didn't want to have typing annotations on the variables that can appear in the code. Okay? Yeah?
Does that mean these are still untyped syntax?
This is typed syntax because I have a piece of code, E, that is of type tau. And this gamma 0 will tell me what the type of the variables are that are free in E, because I'm checking E with respect to gamma 0. This is, so this is fully typed. Okay. Good questions. Thanks. Feel free to interrupt. Okay. Okay. So I want to highlight sort of this difference, right, between a map. Here, sigma is a map between code and code. Over there, if you want to really run it, you have to instantiate code variables with some programs or some program values. So, I mean, you see this is, of course, verbose, okay? So that you can now see why Frank and Rowan sort of collapsed this into one system, okay, where you write essentially on the left side of your turnstile a context stack that models n possible stages you have, okay? And then you don't have to duplicate these rules. But the advantage of a presentation like this is really that it gives you a clear idea, right, what is at the bottom stage, okay, at the lowest stage. It is really the syntax of the simply typed lambda calculus. So, so we're going essentially between these two worlds, right? The world that is code and the world that is programs, and we go between them using box and unbox. I restricted it to 2 stages, so there's nothing like box A. The code is a sub-language of our language of programs, and that's in some sense exactly how quotation is handled in proof assistance, where when you say quote in Rock or in Lean, you get essentially a data type that does not contain quote itself. Okay? It's a pure calculus of construction term. And so knowing what the sub-language is actually really important for pattern matching, because if I now say I have a piece of code that describes a natural number, I know exactly what shape it is. It's either a variable, it's a function, or it's an application. Okay? It cannot be some complicated program that uses some kind of box thing. Okay? That's just not allowed. So how do we get to a type theory? Okay. So we use the same idea of 2 layers. Okay, we have a layer of metaprogramming. Okay, that's not simply typed anymore. Okay, it's actually Martin-Löf type theory. So it has a universe hierarchy and all the things you want. Okay, so type level computation, but it's essentially replacing this outer layer with Martin-Löf type theory. What's the level of code? Well, on the level of code, I am going to actually use something called the logical framework LF, okay, which is a slight detour. I'm not representing Martin-Löf type theory itself or the simply typed lambda calculus itself. I'm representing a framework which allows me to encode these different languages. But the idea will be that I go between these levels, okay, with box and unbox. And if you want to take a sort of a slightly different view, it means you have a dependently typed metaprogramming language. That is Martin-Löf type theory. We have box there. Okay, we have pattern matching on code there. And what is inside the box is coming from the logical framework LF that allows us to represent abstract syntax terms with something called higher abstract syntax, which I'll explain in a minute. And we're encoding these different sublanguages in LF. Okay, so in particular, what I want to do, I want to encode the simply typed lambda characters in LF because that's the language of code that we had previously. Okay. But I can encode in here also systemF, and I could encode in here the characters of construction. And if I want, I can encode session type processes. I can encode propositional logic. I can encode Pressburg arithmetic. Okay, we know that the logical framework LF is very flexible in what it allows us to encode. And that means I get a meta-programming system on the simply typed lambda calculus, a meta-programming system on systemF, a meta-programming system on the calculus of construction. Okay. So what is LF? Okay. So LF is an idea that was proposed in the 1980s by Harper, Hansel, and Plotkin. And then Frank and Conall Elliott coined this term higher order abstract syntax. But essentially, it's a language that is the dependently typed lambda calculus that will serve as a language for representing formal systems. And the idea is that we will model, we will use the function space that exists in here to model binding in our concrete object language. So let me show you. So we had the simply typed lambda calculus. Okay, we had nat and tau1, arrow tau2, and we had terms, acts, functions, and applications. So I'm going to define two types, TP and TM. And here I have nat and arrow as constants. And then I define two constants, fn and app, corresponding to this guy and this guy. And the interesting part is now that fn takes in a function from tm to tm. Okay. So I'm not modeling variables via the Bruin indices. I'm modeling variables by piggybacking on the notion of variable that already exists in LF. So if I want to model nat to nat, then this is arrow nat nat. That's how we would encode it. If you have the identity function, then we encode this as the constructor fn. And then here, this Greek orange lambda is the LF abstraction. And then it returns x. So I immediately get here alpha renaming, just the same way I get alpha renaming in here. I get overshadowing. Okay, so although I wrote here x, an orange x and a blue x, I just use different kinds of lambda abstractions. And here is fun x, fun f applied to x. I get lambda x, fn lambda f, app fx. So the slogan is you model variables from whatever object language we have here, the simply typed lambda calculus from before, by variables in LF itself. And we inherit sort of this notion of alpha renaming from LF, because we know how to do alpha renaming for these Greek lambda functions. Okay, we know also how to use these lambda functions, right? So I can apply this lambda function with another term, and it will substitute for x that term. So I can do this for typed representations, okay, by indexing essentially tm with tp, and I'm representing fn as a function from tma to tmb that will then produce a term of arrow ab. And here you see the notion of terms actually didn't change, and that's because I omitted all the implicit arguments that refer to the types of these terms or subterms, and that can be inferred. So the bottom line is, okay, if you now have LF, which is a dependently typed lambda calculus, you can represent syntax trees with binders. So Dale Miller likes to call them lambda trees, for example. Okay. And this works because these LF functions purely encode variable scope. They don't encode recursion or pattern matching or inductive types. Okay, it's a very weak calculus. And the benefit is you're basically implementing all the binding infrastructure once and for all, and then you're sort of leveraging that. Okay. And this scales to a system, to encoding systems like systemF or the calculus construction, or even to represent typing derivations. So now we want to write programs about these structures, right? I said I want to do pattern matching on these structures, and so the simplest program I could imagine is computing the size of such a term. And now I need to pattern match on this term. So I will pattern match on the substructure, and x becomes free, and then app f becomes free. And so I have these red variables that are basically free variables. And so that would mean, well, pattern matching doesn't fully work. Okay. And the answer here is essentially contextual types come to the rescue. Okay, so if you want to think about how do I characterize what is inside this box, it's useful to think about how I would type such an expression. And we type this expression in a context where we have x. So we have x, which is a term, we have fn, and then we have the rest of this expression, and the whole thing is a tm. And if I want to know what is inside this box, well, it will be a tm that depends on x and f. And so the idea is that we're reifying this typing judgment, right, which is here written with these 2 bars, as an actual proposition or an actual type. So we do this actually quite often in logic, right? So if you think about the implications, implications are the syntax for expressing that something is hypothetically true. Okay? So we might have a hypothetical derivation, but in order to talk about that on the propositional level, we actually use the implication sign. Okay? And if you have a parametric derivation, if you say, this is something that you've proven for a particular parameter, you want to express that as on the level of propositions, you use a universal quantifier. So here is sort of the same idea. Okay? You have a typing derivation, and you want to talk about that typing derivation on the level of types or propositions, and we reify it as syntax. So contextual types reify these typing derivations. Okay? So now I can write this program size. Okay? I can start out in the empty context, and then as I go, I will add these variables to the left side, and everything remains well scoped, and everything remains well typed, if you like. Okay? So in order to give the type to size, we would need to say, for all contexts, if you give me a term in the context gamma, then I will return an integer. And when you want a pattern match, you know exactly what you're pattern matching on. It's going to be an fn, an app, or it's going to be one of these variables that come from your list of variables over here. And for that, we have a special pattern variable. And while I simplified this here to work on an untyped representation of syntax, you can do this on typed representations of syntax. Okay? And pattern matching then is basically pattern matching on higher order patterns. That's also a decidable fragment, and so we trade off essentially ML-style pattern matching to higher order pattern matching. So the general lesson, if you want to model code not with de Bruijn indices, you should model code with higher abstract syntax trees, and in particular, you should pair these trees together with the context they live in, and then you can essentially model pattern variables again as these contextual meta variables, and you use as pattern matching higher order pattern matching. So, so how does this type theory then look like? Okay. So as I said, okay, we have here the meta-programming language that is a Martin-Löw type theory. We'll have a quote, and it will have an iterator over pieces of code. And just as before, we're checking this piece of code by checking M to be a well-formed piece of code. So we're transitioning to the LF level. And on the LF level, T will be a program that could generate a piece of code. So T is a program that generates a piece of code of type A in phi. And we can refine it by applying sigma. Okay? And since we're working in a dependent type theory, A might depend on phi, so we need to apply sigma to A. So now our type theory rules are intertwined, and also our equational theory and our weak-head reductions are intertwined. Okay? So the main challenge then is, how do we actually prove normalization? Okay? And that's what our paper at LIX actually did. Now, another question you might say is, well, how can I now embed, right, the language I've given you in the first part of the talk in this framework? And the answer is yes. Okay. If I would, for example, what kind of code did I have? Well, it was a simply type lambda calculus. So I define an embedding. I map this blue fn to my constructor fn, my application to this constructor app. Variables are mapped to variables. And if I have here a program expression, I need to translate my program expression. Okay. And how do I translate programs? Well, E is already a subset, in some sense, of what I have in Martin-Löf type theory, because these are simply typed programs. So if I come to a boxed piece of code, I need to translate it and map it into my encoding in LF. But the main question is what happens to eval? Okay, and I haven't really talked about eval at all. And the reason is because this Martin-Löf type theory does not have eval. Okay? It doesn't make sense to define a generic eval for this logical framework LF. We can only define eval for specific sublanguages. Okay? But we have pattern matching, okay? And we have what is called large elimination, so computation on types. And that means actually we can implement eval as part of our type theory itself. So we don't need to add it to our type theory because we can define it. Okay? And the idea is that we define essentially a function reflect that would take in one of these syntactic representations, so for example a nat, and it would reflect it to the type that we have in our Martin-Löf type theory, namely nat. And if you have arrow ts, then you reflect t. This is the arrow from our Martin-Löf type theory, and you reflect s. And the eval function will pattern match on these terms that have a type A, and they live in a particular context gamma, and we're going to reflect them to terms of type A, okay? Of reflect A. So if A is nat, this part here is a term of type nat, and we're going to return an object that is of type nat. Okay? Now the main thing that we still then need is what happens to these variables in gamma, okay? And that is essentially a function that will map the LF variables. Okay, so this is one of these LF variables. These LF variables that are of type B to values of their corresponding type. So if B is a nat, a TM nat, it will reflect it to some value in Martin-Löf type theory that is type nat. Okay. So that means we can actually adequately represent, in this case, lambda box in Cocon. Okay. And so now you have a framework where you, of course, can not only represent simply type lambda characters, but you could say, well, I'm going to represent system F. Now, for system F, you can't write such an eval function, okay, because system F is actually not a sublanguage of Martin-Löf type theory. Okay, it has impredicativity, and Martin-Löf type theory doesn't. Okay, so you cannot write an eval function for all languages. Okay, but for some, you certainly can, right? So we proved normalization and consistency of Cocon using sort of a standard method of logical relations. If you're interested in that, you can read that paper. We have given a category theoretic foundation for this together with Jason and Ulrich Schirp. And it turns out that Cocon is actually the syntax of a paper that has been written probably also 15 years ago by Martin Hoffman, who gave a semantical analysis of this higher obstacle syntax idea. But there was never really a type theory to sort of express it properly. And in fact, Cocon is that type theory. Okay. Now, the next step we might ask is, well, can I use this? Okay. This is in any form available. Can I implement this? Okay. And so at the moment, this is not implemented. So then the question is, how would I implement it? And there's sort of a choice, right? Normally, like how we implemented Beluga or how Agda is built, right? You look at your type theory, you've proven your properties, and then you choose your favorite programming language, right? In Agda, they choose Haskell. In my case, we chose Beluga, and then you define a data type in OCaml that represents this, and you implement your typing rules, and you make certain optimizations to make this work. Maybe you use more an explicit substitution calculus that deviates already a little bit from your theory, okay? But it's sort of unsatisfying, right? Because as you start implementing, the implementation will deviate more and more and more from your actual theory. And in fact, that's the reason why BetaCoq was created. We wanted to narrow that gap, right, between the theory and what was actually implemented. So we took a very different step here. Okay, we basically decided that we would build a correct by construction type checking kernel, and we started with Martin-Löf type theory and Coq. So we described declarative typing and declaratively this normalization by evaluation algorithm, so a slightly different proof technique. We mechanize this typing and algorithm in ROC. We implement also, we prove properties about this normalization algorithm. We prove it, for example, to be normalizing. We implemented an algorithmic typing and functional NBE. In fact, a lot of credit goes to Claire here. And then we extract from it a core kernel, a type checking kernel to a camel. And then you can use this as a trusted backend. Okay. And the goal here of this work is both to extend it to Cocon, as well as to provide a trusted backend to other type checking systems, such as Martin-Löf type theory, or other type theories, okay, that we want to then explore. So it's also meant as a kernel for exploring different mechanizations of type theories. And if you're interested in that, you can talk to Claire, and we also have a talk on Saturday. Now, we also looked at other extensions of this meta-theoric framework. So in particular, we looked at how to do meta-programming on System F. So that is also work Claire has been involved in. That was at POPL in 2022. And it does support pattern matching on polymorphic code. It supports nested boxes, but there's no normalization proof. Okay. But it does represent essentially code in this Hua style, okay, without the embedding, but more directly. And then very, very recently, so Jason is a PhD student of mine who has graduated just in November. And here we have developed a Martin-Löf type theory that has also layers, but it actually has really directly you pattern match on Martin-Löf code. So there's no notion of Martin-Löf type theory in LF or anything like that. You basically have Martin-Löf is your syntax, and Martin-Löf, we can also pattern match on it, but in particular, you get different equations on the code, or on the type of the code, or on the meta-programming setting. And so we've proven, in fact, that the system is normalizing. And this work here is sort of extending this original work by Frank and Rowan. That was a Kripke-style modal type theory, unrestricted, n stages, okay, and builds an intuitionistic type theory around it. But here we don't do pattern matching. Okay. And the other two projects I want to mention is essentially research that we are doing in generating code that represents session type processes. Okay. Then you have two completely different languages. You have one that is your meta-programming language, and the box, the code that you're describing are essentially processes. And then sort of even further, if you want to talk about different layers of sub-languages, okay, we've been proposing a system that uses not box, but uses something called an adjoint modality. And that gives you sort of a very flexible way of connecting different languages, and it moves this framework almost to an infrastructure for interoperability. So there are a couple of lessons, I think I've learned along the way. One is that I do think contextual higher order syntax is a good way of representing code. There's no reason we need to expose to programmers the underneath gory details how we're representing variables. Okay. We like higher level languages, but we don't work with low level representations, right? Why should we expose it when we work with code? Syntactic structure of code. Layers give us a way of syntactically characterizing the code and distinguishing it from the meta program. And moreover, these layers actually allow us to control operational behaviors and equivalences. Okay, so we might have different equivalences on the code versus the program. For example, 3 + 4, if it was a part of your code, it did not reduce. It was on the level of program, you do reduce. Okay? And pattern matching gives you the ability to actually evaluate code. So if you have the ability to have pattern matching and you have a rich enough type theory, you don't need eval in your metaprogramming system. You can define it. Okay? And Cocon is sort of a language that prioritizes sort of the representation of different languages that then kind of interoperate. Okay? So that's a design decision you make at some point along the way. All right. Well, thank you. I'm happy to take some questions. Yeah.
Thank you. I like the talk. I'm very interested in metaprogramming, and one of my favorite examples to figure out how to type check, it comes from Racket, where a lot of Racket code manipulates binding. It's not merely lexical binding, but you may export things. But my favorite example is struct in Racket, which generates several bindings using basically an algebra on identifiers. And I have no way in Racket to predict and say like what I expect such a macro to do, like how it will manipulate binding, what names it will export, and how are they calculated. And I'm wondering if you've thought at all about this problem. Like, how do I not only say I expect something to be in scope, but I expect several identifiers to be created following a certain pattern?
Yeah, so I think if you have large eliminations, you can more talk about the different types you're actually creating. So there's on the template Haskell website, there are similar problems, and they work very well on the untyped setting. And the question is, how do you do that in a typed setting, right? And essentially, it's a slightly different problem, but I think it's similar. Okay, so what they wanted to define is sort of generate code of functions that have n input arguments, okay, depending on the first number. So I want to generate a function that, and maybe even paired them, okay? So I have a pair, I have one argument, I have a pair of 2, a pair of 3, a pair of 5, and so on. Okay. And that is not necessarily easily typed in a simply type language, right? So for that, you need a richer type system if you wanted to express that.
Okay, thanks.
Yeah, thank you very much for the great talk. Really appreciated it. So you're using higher order abstract syntax to represent the binding of the meta language, right?
Okay, LF is my meta language in this case, and then it's the binding of my object.
Yeah, because it gets kind of confusing.
Right, so let's say if I have OCaml, I would represent the bindings of OCaml with bindings in LF, yeah.
So, but anyway, so my question is, so there's also like this lesser known idea floating around for a few years, instead of using de Bruijn indices, using co-de Bruijn indices.
Right.
I don't know whether you're familiar with
that.
Yes. Do you know whether it would be would also fit in your framework using co-de Bruijn indices, or is it like even worse than pointer index arithmetic?
I've been on record saying, and I'm saying this again, that I passionately hate de Bruijn indices. Okay, although I have been using them, of course, in all our implementations, and co-de Bruijn indices, in my mind, are even worse. Okay, because I mean, they were originally, I think, proposed in the setting where you have substructural systems, right, where you need to separate your context, and then it becomes sort of not meaningful anymore what its reference is. And so when you think about a linear type system at the axiom level, when you look up a variable, there's only one assumption. So of course, the number of this variable needs to be 0, right? And so what happens now if you look at the representation of your term, all variables will be 0. Okay, because they're always typed in a context where you only have one variable, so the index will be 0. So reading a co-de Bruijn term is even worse than reading a normal de Bruijn term, okay, in my mind. But
I was wondering if there are any applications also to data type generic programming of this approach.
In what example, or what do you have in mind there?
Like basically having some products or something like that for data type and generating functions based on that.
So I guess the best case I can say is in this work, in the first work here in Mint, we give several examples of how we would work with sums of products like that, if n-ary sums, for example, and how to do metaprogramming for that. So These are some of the examples we've been using, and you really require the full power of dependent types to express the typing invariances for it.
Right, thanks. Okay, thank you.
Oh, yes, yes, yes.
Okay, type program analysis without encodings?
Yes, yes.
If I can see properly, go on.
Right. Yes, so the comment was just made that I'm an amateur now. I used to be a professor. I stepped down from the university so I could get more research done. And it's true, it actually worked, yeah? But I do get more time for walking as well. And living in Sydney, I like to walk around Sydney Harbour and sometimes take a photo. Sorry, yes. So I do like to take a few happy snaps. So that's a nice day in Sydney. So my title today is Typed Program Analysis Without Encodings. And I really enjoyed the Brigitte's talk. And but I'm not smart enough to do that kind of stuff, right? So we have a lot in common. We're doing typed program analysis. Brigitte was saying that metaprogramming is programs that produce programs. And I think that's right. But isn't that what higher order programming is supposed to do? Yeah. So the thing that makes us different is that I want to do away with the encodings. No quotation. Yeah. On a couple of the slides, Brigitte had the extensional side and the intentional side. And that's the key, because lambda calculus and our lovely favorite functional languages and the rest don't do intentionality. And that's where all the problems start. So I want to show you today a calculus where intentionality is first class. It's baked in at the beginning, and so everything's become simple enough that I can understand. Right. Yeah. Yeah. So at the heart of all of this is the idea that programs have a dual nature. On the one hand, they're functions. They take inputs, they produce outputs, and we often think that that's their primary nature. But if we're doing a partial evaluation, program manipulation, metaprogramming, well then we want to think of them as data structures on which we can do pattern matching, that we can manipulate them and change them in that way. So how do we reconcile these two natures? One is to introduce a meta theory of quotation, boxing and unboxing that gets us back and forth. But now, what happened to the idea that there's only one notion of computation? The Church-Turing thesis says there's only one way, one kind of computation. How come we suddenly have two? Yeah. So that's a bit unsatisfying. But the usual approach is to say, oh, our programs are functions, and we'll do this quotation to get out some syntax. But we can turn that around. What if we say, oh, let's take the data structure as the primitive thing. How can I impose some functionality on that? Well, the answer is do some algebra. You add some equations to explain how those things work. Yeah, so if we look at combinatory logic with its operators S and K, then we can think of the things like this S, X, Y, Z. We can think of that as a syntax tree. It's got a root labeled by S and 3 branches, X, Y, and Z. Yeah, and when we want to manipulate that and evaluate it, then we end up with a new syntax tree where we're attaching branches to the root of X. So we have this working already. So why don't we go that way? Whoop, I seem to have, right. Well, the biggest argument is that these operators S and K are artificial. I might want to add in an identity operator or some other B's and C's and whatnot, yeah? But since there's only a finite alphabet, each of the letters S and K and the rest can themselves be represented by small trees without any labels on them. So we can take any syntax tree in any language and replace it by an unlabeled tree. Well, these unlabeled trees are natural things. Just as the numbers are natural and can be represented by beads on a string, these natural trees are also well-formed semantic objects. Yeah? Nothing human about them, nothing artificial. They're natural, yes? So now we can say, okay, our programs are going to be unlabeled trees, natural trees. What kind of equations, what kind of algebra do we want to put on those things? Well, if you think that this little subtree represents S and this one represents K and so on, you can write some complicated algebra to describe their behavior. But now that we understand that we're working with these unlabeled trees, let's start over, let's start fresh. So the nodes, these unlabeled nodes, represent a single operator. Instead of S and K and the rest, these unlabeled nodes are the unique operator. And I like to think of Leibniz and his notion of monads, that everything in the world is built out of combinations of a single monad, yes? Well, it turns out you can write some nice rules for these things, and you can build some interesting trees and do some interesting computations. Too many fingers again, right? So here is the frontispiece from my book. It seems to have it's not. You can guess what's at the bottom, yeah. But well, I don't imagine anybody's going to pass this thing exactly. But you can build up interesting trees. This here is a self-evaluator, an eval in the sense of a meta computation. Yes, so this really is a working program, and we don't need any encodings because it can be applied to itself without any meta theory. Yeah, I'll just take a moment to describe how this tree works. The colors are not part of the semantics. They're there to help us, yeah. But this green bit at the top does the recursion. And this red bit here does the case analysis. And if we keep going down, you can see 3 green branches. 1, 2, and there's a tiny little one there. Those are the 3 branches of the pattern matching function. I have 3 branches because all of my data structures, all of my values are binary trees. So either they're a leaf with no branches, or a stem with 1 branch, or a fork that has 2 branches. So I need 3 cases in my pattern matching function. And of course, when you're doing evaluation, you impose a strategy. So this is a breadth-first strategy for working over the trees, something like an eager evaluator. And this red bit at the bottom, that is the eagerness. That's the strategy. Yeah? So all of this goes rather directly. And this is the subject of a book I wrote after I retired, and called Reflective Programs in Tree Calculus. Yeah? So I built all of that up. That was the key ideas were done by 2019, and nobody would accept it for publication. So I got a book contract and I wrote the book, but then the publisher couldn't find anybody to write a review. Yeah, it's too crazy. Yeah. So a friend said to me, look, I don't really care about self-evaluators, that's boring, but if you could do a typed one, that would be really cool. Yeah. So in 2021, I said, okay, how long can it take, right? And now here in 2025, I want to show you a type system for this calculus. Yeah. Well, before I get there, I should say that there's actually at this stage 2 variants of tree calculus. Everything I've said till this moment is the same for both of them. The original one in the book gave the tree that's there, and the goal was to have just 3 reduction rules, one for leaves, one for stems, one for forks. And I did some trickery to make that work. Well, Johannes Bader has been, we've been in conversation for a year or so now, and he's been keeping me honest and making useful suggestions and things. And he said, but it'd be so much simpler if you just used 5 rules. And I'm going, 5? That's a big number. He's going, no, it'd be simpler. So these days we're working with triage calculus, and here are the 5 rules. So the first one, so this node operator is a ternary operator, and it's intentional. It looks at the structure of its first argument. So if the first argument is a leaf, then you take y and z, return y. This is just like K of combinatory logic. It deletes something, yeah? And if the first argument is a stem, then it copies something, just like the S operator of combinatory logic, yeah? So in these first 2 lines, we have all the power of combinatory logic, that is to say, all the power of lambda calculus, the ability, Turing completeness. We can do all the arithmetic, yeah? But there's more, right? So we can ask, what if the first argument is a fork? Well, if that's the case, then by the time we get to when we look at this fork here, the program, then there are 3 subterms, W, X, and Y, and they will provide the cases for the pattern matching. So now we're going to analyze the third argument. If it's a leaf, then we use the first case of the pattern matching, we use W. And if it's a stem of U, then we use the second case, X, and we apply that to U. And if it's a fork of U and V, then we take the third branch of the pattern matching Y and get YUV, yeah? So these last 3 rules here are called triage, which is a pun on the tree calculus and the fact that there are 3 kinds of values, yeah? And that was a rather elaborate construction in the original tree calculus, but now it's just baked into the reduction rule, so everything becomes a bit simpler. Yes?
So these triangles are ternary?
Yes.
You probably need to repeat my
The triangles are ternary, yes. Ternary operator.
Ternary operator, but the inner pattern match you have there, you only have the case of a triangle that takes 2 arguments. You don't have the one where it takes 3.
Right, this is a combinatory calculus. So when I say a ternary operator, it can be applied to 0, 1, or 2 arguments without any reduction. When you apply it to 3 arguments, then reduction rules apply.
So if I understand correctly, is this working?
a monad or a combination. Here, every program is either a leaf or it's an application. So I just need 2 type derivation rules for those things. But I'm going to use subtyping to gain expressive power. So whenever the leaf type is less than some type T, then the leaf node has type T. And application rule is just the usual thing. So you've got a bog standard rule for application, and leaves have type, nodes have type leaf or some supertype of the leaf type. So all of the expressive power is focused in on this subtyping rule. Yeah. Well, if we're going to turn leaves into stems by application, then it better be the case that the leaf type is less than a function type. And the obvious thing, least obvious if you have a moment to think about it without some guy rabbiting in your ear, the obvious thing is that if you get a branch of type U, then leaf applied to that will produce something that's a stem with a branch of type U. So there's how to turn a leaf type into a function type. In the same way, if we have a stem of type U and we apply that to a branch, we want to get a fork. So stems are a function type into fork types. So now at least we can build up our binary trees from leaves. Okay. Well, we've got function types there, so we better do the usual thing with those. They are covariant in their result types and contravariant in their argument types. And this is enough to give us subsumption. Even though our subtyping is focused on the leaves, we are able to get subtyping to apply quite generally. We don't need a special rule for that. By focusing all the subtyping on the leaf types makes the proofs a lot easier. Yeah. Well, we've got started, but what are we going to do about the reduction rules? Well, it turns out that each of the reduction rules inspires a subtyping rule to relate the left and right-hand sides of the subtyping. So if we have a node applied to node and some x and some y, well, the node x becomes a fork of a leaf and something. When we apply it to some other v, we toss the argument of type v away and keep the argument of type t. Yeah. So this is the K reduction rule of tree calculus. The information in that rule is captured in this subtyping relation. Yes. The second rule, if you're captures the properties of the S combinator. If you're familiar with the S combinator, you see here's the arguments of type U to V to T and U to V, and the result is of type U to T. So if you've done any combinatory logic, then this will all be a bit familiar. The F and the S are used to build up the type of the left-hand side from the types of the arguments. And in the same way, with a little bit of thought, you can produce rules for triage. Yes. So I'm not sure that staring at them for another 30 seconds is going to make it much clearer, but each of the reduction rules inspires a typing rule, right? So from this, we can see that K is of type U to V to U, S has its usual type, and you can define the identity in terms of K and S, it gets its normal type. So all of the things you do in simply typed lambda calculus or combinatory logic are all working as expected, yeah? So what about recursion? What about fixed point functions? Well, in lambda calculus, recursive functions don't have normal forms. Yeah, y of f can reduce to f of y of f, and there's no way of getting around it. Yeah, but in tree calculus, all of our programs have to be binary trees. They have to be normal forms. So what's going on there? Well, the interesting thing is that although we traditionally think that all these models of computation are equivalent, they're not equivalent in some interesting ways. So in combinatory logic, every combinator is equivalent to one in normal form. And the reason for this, I haven't prepared a slide on this, but if you think about the eta expansion, that m goes to lambda x mx, and then you do a very naive interpretation of the lambda abstraction back into combinators, it splits apart every application in the original argument m. So every combinator in combinatory logic is eta equivalent to one that is in normal form. So in lambda calculus, there's no escape the fact that fixed point constructions have no normal form, but even in combinatory logic, we can do that. And we use the same kind of tricks here. And the heart of it is this weight operator. So in combinatory logic or in tree calculus, you can define an operator. So weight2 says, give me 4 arguments, and then I'll do something. If you only give me 3 arguments, then I'm going to wait till I get another one. Yeah? So that's this decomposition process played out. So now we can define a fixed point operator Z as a weight, and we have to massage the usual account of fixed points to take account of weighting. But now we get a fixed point construction which is in a binary tree, which is in normal form, and that's all good. So if we think about trying to type that thing, now we're going to use the fact that every program has a tree type. So if you think about this little omega from the previous slide, it has a tree type that has exactly the same structure. And if we want to give a type to the fixed point functions, just in the same way that we used our knowledge about the reduction rules to do subtyping there, we can use our knowledge of the correctness of the fixed point construction to add a subtyping rule that reflects that. So here's the subtyping rule that supports typed recursion. So omega 2 is just a tree type, but it can be thought of as a tree type from itself to the type we need for building fixed points. So if you think about self-application in a fixed point construction, or omega applied to omega, that's captured here by the subtyping rule. So the motto of the system is that the term language is going to be fixed. It's just these binary trees. But if we want a more expressive type system, we don't hack the term language. We don't add in let terms or boxing or new kind of variables or type applications or whatever it happens to be. There aren't 1,000 versions of tree calculus. Yeah? Instead of hacking the term language, we're going to hack the type system. And the thing we have to hack the most is this subtyping relation. But whenever you give a proof that some term has some nice property, that given an argument of a certain type, the result will be a certain thing, then my experience is that can always be encoded as a subtyping rule. That's how you improve the expressive power of the system. So in this talk, I'm going to show you 3 examples of this kind of hacking to get things done. Yeah, so that's fixed points. So now we can type all of the mu recursive functions on natural numbers. Yeah. Again, Brigitte and I are both talking about the size function. Yes, and it's a pattern matching function. Yes, so in pseudocode, we can say that the size functions of the size of a program P, well, if it's a leaf, then the answer is 1. If it's a stem, it's 1 plus the size of the branch. And if it's a fork, it's 1 plus both of the sizes. Yeah. Well, triage captures this. Here is the same program written out. The Z is the fixed point. Then we take an argument. There's a recursion argument, and then we do the triage, and there's the size program written in tree calculus. Yeah. What about the typing? Well, if we look at the type of the tree type of that program, at the heart of it is this fork type. So the triage has got 3 branches. It's a fork of a fork. And the first one is the number 1, which is of type nat. And the second one, I've just thrown in quantified types without telling you. That was in the ... earlier, right? But the second argument will produce a nat from 1 argument, and the third produces a nat from 2 arguments. So we have to turn this into a subtype of the expected type of size, which says, given 1 argument, any argument, give me a nat, right? We could just make this a subtyping rule and everything would be fine. But in fact, size is just an example of a generic query. We can write generic queries for equality or looking for a subtree of a certain shape or whatever it happens to be. So we can generalize this rule. We need to have the notion of covariance to take care of things. But the general form of the rule for generic queries says if the branches for leaves, stems, and forks are all coherent in some sense, then if we can type what's happening on leaves and stems and forks, then we can type everything. So the notion that every value is a binary tree gets encoded up into this rule. It's a little bit heavy to write down, it's in the paper, it's in the book. Not the book doesn't do any types, but you've got the spirit of it here, yes? We've written a subtyping rule that captures the notion that every value is a binary tree. Yeah. Well, the third example today is a self-evaluator. It's called BF because it does breadth-first evaluation. You never evaluate a node until all of its branches have been evaluated. Yeah. And it's a pattern matching function. It's given a program f, a function f, and an argument a. You look at f. If it's a leaf or a stem, then you just immediately build the data structure, the stem or the fork that comes out. If itself is a fork, then you have a look at what z is, and if the program is actually k, then you return y. If it's a stem, then you have to evaluate xa applied to ya. And here's the function eager that I mentioned earlier, which is ensuring that bfya gets evaluated before you evaluate the rest of it. Yeah, and then you just follow your nose, take the naive account of what a breadth-first evaluator should do. It comes as a pattern matching function, and then you can encode that as a tree. Yeah. So here it is written again in more formal kind of tree calculus. When it comes to typing this thing, we end up with a conditional typing. If this fork type FUV can be a function type, then we can get a function type for this other argument. Well, I didn't want to do conditional typing. I'm not smart enough. Yeah. So I hacked the type system again and introduced this type constructor A, which is as function. So it stops anything happening to that type until it proves to be a function type, and then the obligation's discharged. So doing things that way, we can give a type for, and adding some new subtyping rules, we get a type for BF that takes any Z and produces an A of Z. When you specialize Z to a function type X to Y, we get this very elegant type for the breadth-first evaluator. It takes a function and an argument and returns something of the result type. Yeah. So this is working in system F plus some tree types. Not system F omega, not system F omega with some tower of expression types and boxes and things on top. It's just a slight extension of system F, yes. So using triage types, the breadth-first evaluator shrinks. And Johannes was very keen to make this thing smaller, and he kept saying, I've got a smaller tree for the breadth-first evaluator, and then I had to go back and rehack the type system. Yeah, so he was, cracking the whip there, right? Anyway, this self-evaluator has 392 nodes. Yeah, Johannes has one now at 352 nodes, but I can't type it. not yet. So so that's the story there. I have a slide about the church Turing thesis, but since the chair has stood up, I'm thinking, ask me a question if you like, and have some conclusion stuff. But should I go through the conclusions or stop now?
Yeah, and it's already 3 minutes over.
Oh, excuse me. Right. Okay.
Yeah. Thank you very much.
Yes.
Very quick one. Well, I can just speak loud. Yeah, yeah.
It needs to be in the mic so that people I see.
I was just curious if the tree-based structure allows you to do any special graph theoretic properties, or if it's more of a conceptualization for the user.
The tree structure is there because I want to have a single operator. So as soon as I commit to a combinatory calculus, I've committed to the trees.
Gotcha.
Yeah?
I think we should move on. Sorry for that.
Sorry for the delay.
Okay, so I'm going to start with some unreadable system T code. Does anyone want to tell me what this function does? Okay, it does a sum. What is it summing over? A tree. What type of tree is it summing over? You've got the type of it, so that should help. So it's summing over a binary tree of natural numbers. But the type of the binary tree is nat to nat to nat to nat to nat. Why? Well, this is all due to type encodings from regular types down into system T. So in this talk, I'm going to mostly be talking about type encodings for system T, and then I'm going to go on and explain how you can use this to write a fueled self-reducer within system T. So giving a practical application for this. The type encodings are not new. They are work by Oleg Koselyov and John Longley and Dag Norman, but applying them seems to be new. So here's this unreadable system T code again. And if you have a look here, for instance, we have tree is applied to 4 arguments, and tree is applied to 4 arguments, and tree is also applied to 2 arguments. It seems to be doing 2 different things here. And if you look over here, we have heap is applied to 3 arguments, but it's also applied to 1. So it seems to be encoding 2 different types in the same structure. So what it's doing is the tree and heap are both encoding union types. So these are C-style unions. So they have injections and projections. So you can put data in and take data out. If you take out the same data you put in, things work well. If you take out different data, things work badly. Luckily, we'll get to remove these later on in our encoding process, but for now, we need them. This encoding is thanks to Oleg Koselyov, and the exact structure of the projections, injections, and union depend on the types of what you're injecting and projecting from. This is only possible because system T only has functions and natural numbers. If it had any other type, this union type would not exist. So using union types, the type of sum is now significantly harder to understand, but the code is somewhat easier to understand. So a tree, it takes a left out of it for the depth and the root, and it takes a right out of it for the heap. Similarly, for when we're looking into the heap, we take a left out of it to get a tag, and we take a right out of it to get a union. But here we can see that for the depth, root, and heap, we both apply different numbers to tree and then do a projection. And for tag and data, we apply different numbers to heap and project out the data in different ways. So this is encoding product types. So a product type is a function from a natural to a union, where if you give it the function 0, then you have a first, and if you give it a 1, you get a second. So this is, again, an encoding thanks to Oleg. So using product types, the code gets a lot easier to understand again. So we first deconstruct the tree here, and then we then deconstruct the heap argument later. But Here we have an if statement based off of a tag. And on one case, we do something with the data. And in the other case, we do something else with the data. And this is tagging a union. So some of you might be thinking, tagged unions, that sounds familiar. And that's because a tagged union is just a sum. So you can encode tagged unions using some, or you can encode sum types using tagged unions, a pair of a natural number and a union. It's a left if the tag is 0. It's a right if the tag is 1. And to do a case split, you first check the value of the tag and you apply the corresponding function. So using sum types, the code again gets somewhat simpler. We first deconstruct the tree, and then recursively, we match the value of the heap. And if it's a left, then we just return the data. And if it's a right, then that must be it's a branch. So we recursively find the sum of the tree. But it's a bit confusing how we do this, because we have a tree is a combination of a depth, root, and heap, whereas normally we just want to have a single data structure we fold over. So we need to have these 3 arguments because, as the name suggests, a tree is just stored as a heap. So each individual recursive argument is represented by a natural number that points somewhere else in the heap. We need to store the depth of the tree so that then we can do primitive recursion over it to compute the fold. If we didn't know the depth, we couldn't have a terminating program, and systemd has to have termination. And then we also store the root of the heap for efficiency reasons. So say you only want to do a case split on the outer structure of the tree. You don't want to actually do a full fold. If you didn't store the root, you would have to do a fold over the tree anyway, returning a sum type, and you have to rebuild the tree as you go all the way back up. So by storing the root, you don't have to recompute the tree every single time. You can just do it once, and that's good enough. So our final program for summing over a binary tree is, as you'd see, a sum over a binary tree. Very simple. So all of these encodings are computable within systemd, and you can also, so you apply them in the reverse order. You start with this nice language and end up with the unreadable systemd. So there's only some types, inductive types this works for. These are the regular types. So examples of regular types are lists, binary trees, finitely branching trees, and so on. So 2 non-examples. The first one here is a really badly behaved type. It's not even it's not strictly positive. It doesn't even have a fixed point in set. So for all the models that systemd supports, we have no chance of representing it. The second one is for countably infinite trees. So these are ones where each branch can have infinitely many children. The reason why we can't represent this in systemd is because you can't compute the depth of the tree. If you're given infinitely many children, you need to find out the maximum depth of those children to be able to find the depth of your new tree. You can't compute the maximum of an infinite amount of data in a finite amount of time. So we can't represent this data in systemd. So using these data structures, you can represent terms. So a systemd term is either a variable, it's 0, it's successor, it's the primitive recursor, abstraction, application. Pretty standard representation of terms. We're representing variables here using De Bruyne syntax because that's what we have in systemd. Other things would work, but I don't know how they would. You definitely can't do HOAS, though, because that isn't a regular type. So using this, you can define a parallel reduction step. So this takes all the beta redexes in your term and reduces them at once. It has to do it all at once because you do a fold over the tree. You can't just stop at the first one unless you have a more complicated data structure or a more complicated function. This is actually the simplest one. I'm slightly abusing syntax here. So in my fold, I'm doing a fold and I'm doing a pattern match at the same time. You can separate it out into 2 steps. That won't fit on my slides. So each step of your fold, you do the obvious thing. So if you have a primitive recursion and your target is 0, then you take the 0 branch. If your target is a successor, then you do an application. And for an abstraction, you do beta reduction. This substitution function is also definable within this nice type system. So using all of these things, you can iterate this step function to end up with a fuel self-reducer. So this takes a fuel function, n, an amount of fuel n, and a term, and produces a term in the normal form if it's given enough fuel. This is somewhat unsatisfying. You would want it to be able to compute the fuel itself. Unfortunately, that is impossible in System T. It's proven impossible by Andre Bauer, because that way you could come up with the fixed point for successor, which doesn't exist. So here is how you can use these fancy types. I'm currently working on extending. So I said that the compilation program was definable in this type system. I'm currently working on actually implementing that translation within it. And then I've written a compiler from this fancy language into Scheme within Idris 2. This is a verified compiler. So it has a proven, or it proves that the term is well typed as it computes the types and does the compilation steps. And the goal is to end up with a efficient program that takes these these fancy terms, which I've called primrose, and reduces them down into System T. So in summary, you can encode the regular types within System T. You can use these to construct a fuel self-reducer, and I'm currently working on implementing this translation within this encoding itself. Thank you.
What kind of other programs can you write in System T? Because it seems to be the compiler constructors want to always write like a reducer for, you know, like a compiler in the language itself, but
so you can, as System T is a subset of this Primrose language, you could write a self-normalizer for System T via this encoding directly. I don't know of any other applications for using System T other than it's a really small language, so it's a really good place to test ideas on. So you don't actually have to use System T as your target language. You can use this nicer one and its equivalent.
All right, thanks.
In your representation of System T, the representation does not have any types, right?
So the representation of System T here doesn't have any types.
Yeah.
To be able to do the compilation step, you do need type annotations. It's not hard to add them to this syntax, but again, it'll just make the slide longer.
Yeah. Okay. I mean, I'm just curious whether the adding type constructor will help in terms of fewer, because there is. I guess we already know that the paper called the break to the normalization barrier, which uses type annotations to solve the problem of normalization barrier. So I'm just wondering whether it also helps here.
So unfortunately not. The type system of System T doesn't let you do any case splitting on what types you have. So even if you had imperfect information about your types everywhere, you'd still have to apply the same function throughout. So if you had some form of dependent types, like breaking through the normalization barrier does, then you can actually do some self-reduction without the need for fuel. But here, that's impossible.
I wanted. I think there is a work on typed self-representation thing. So whenever you want to write a self-reducer, it is rather easy to do it in untyped thing. But if you introduce types, then I think there is a lot of. I think there are a series of papers by whom I couldn't remember, but I wonder if there is any connection to the work there.
So this is a typed fueled self-reducer. So all the problems of overhead for representing typed self-reduction also apply here, with the added benefit of having to compute the amount of fuel you need to reduce as well. So it's even less efficient in some sense.
Any other? We have some more time. Okay.
It's more about motivation. So why do you choose the system app as a target for this project?
So, long story short, I was trying to do something else, and System T was a nice, convenient place to start because it has natural numbers and functions, and that's all I needed at the time. And through a long series of extra steps, I ended up writing a self-reducer for it. And when I wrote that self-reducer, I used these type encodings. So it's an accident that this happened. It wasn't an intent.
Okay. Thank you very much. We'll back in 20 minutes.
Yeah, come back for that. It's like a kind of at the end. Extreme.
Hello.
Yeah, I was trying to look at the talk title.
Hi, we are hearing you and seeing you. So now
Okay.
the session starts with
Can I
with
start?
the introduce. Can you wait a minute?
Okay. All right. Let's start
Yes.
the last session. Okay. Yeah. The first talk is a remote. That's our second one, and it's a short talk. And another talk, I will start with panel. Okay. So next talk is type-sensitive algebraic macros. Who's giving the talk? April. Okay. All right. Please start.
Oh, hello. Good afternoon. I'm April, and I'm giving this talk on type-sensitive algebraic macros. It's work with Robert Octigi from the University of Strathclyde. So I'm going to start telling you that the goal of this project is to introduce metaprogramming with algebraic effects and handlers to language with dependent types. But here I will start working with the well-known SDLC. Some people in the audience might have heard something in the lines of what I'm going to present. It's because Robert Atke has already presented this about 10 years ago. So we are picking it up again. So let's get started. So let's start by having our simple SDLC type checker. And then rather than having it in your regular implementation as we would do in Haskell, we slice it, and rather than pattern matching on specific constructors, we have each of the constructors being its own function. And we also add a couple of other constructors like have, which means to assign a type to a term, and has type, where whether in this case where you can assert what a term has this type, and then now we have type checker operations. Now with those operations, we can write some programs. Here we can write a program that is just an assertion. We first assert that it has a specific type, and then we write the term for it. And the second example, we have the same assertion, but it also has a hold that we can pass in another term. And we can have multiple assertions with holds. And then looking at those programs, you may ask yourself, wait, are those macros? And the answer is yes. Not only because it was in the first slide, but that's what we are trying to get done here. So, but now let's get serious with the work we are doing and start implementing those algebraic macros in Agda. Here we have, again, the algebraic macros for SDLC. In Agda, I have highlighted some of the implementation, just showing you the types and how it would work. And with that, we can start to write programs like this one, where we can assert a goal. The definition of goal is shown on the first line. And we can basically show that this term has this type. And also we can, with this macros, we can also start introducing tactics that are well known in a programming language like Rock. So we can here have intro where we introduce a variable v1 and v2, and we have and to prove the application we have the assumption. So I want to make it explicit here that we are using a higher order abstract syntax, and we hide universe levels in Agda. If you're looking at this code and thinking, oh, this is not going to work, it's because we have removed the levels to make it easier to read. So we have implemented this, and can we do more than type checking with this? And the answer is yes. We can implement elaboration as well. And here, giving a list of types, we may have a type and a new term that is type correct. And right now you may thinking to yourself, how would this scale to other type theories? And my answer is, of course, in a sense that I'm hopeful that I can answer this, but we are in the process of extending this to other type theories. But here I can show you that it works for the bidirectional SDLC. For those who are not familiar with bidirectional, the idea is that type checking has two judgments. One that the terms can be checked against a type, and also that giving a term, you can synthesize a type for that term. And here we add a switch and ascribe, which are operations that are related to the that are necessary for this bidirectional implementation of SDLC. What we gain in this when we do this is that we no longer need to talk about what the goal is and what the term is. We can just use introduction and goal. And one application for this is was shown in eCoop 2014 by Omar et al. That if you have different types of constants, for instance, a string that you want to interpret it as HTML or Markdown, so you could implement this elaboration in using our algebraic macros. You might be asking yourself, what is algebraic about this macros? And the answer is that it basically forms an algebra of a type theory. So we have our operations that vary depending on the type theory. And we have equations. Here the equations have a little alert emoji because we haven't proved that those equations hold for this, but we are in the process of doing it. And also we can extend it to contain models, and models are another name for handlers. So the idea of algebraic macros fit perfectly the theory of algebraic effects and handlers. Now let us go one step up and implement this in a type theory that has unification. Here we do it by implementing macros for prologue style inference. And here we introduce meta variables. And we are able to introduce those new meta variables to the context with the new operation, and we have the unify operation that unify two types, and choice that is very common in prologue style inference. with that, we can write a tactic by assumption where we can search for this unification and choose whether to unify or continue to search along the context. So with this, we can show that our system is flexible enough to do more interesting stuff than SDLC. So in the future, we are working on, as I said before, show the equations for each theory pod. We also have started extending this for system F omega, and finally we want to extend this for dependent types. Finally, if you want to see the implementation, it is on GitHub, and we have as well a playground programming language that we are implementing this and other stuff. And this playground language is implemented in collaboration with Juan Coca, and who was an independent researcher, and Paulo Torres from the University of Kent. You can use this QR code to get those links. That's it for me. Thank you so much.
Thank you. Any questions? Okay, let me start with one, actually. So you started with saying you picked this up after 10 some years. What's the motivation for that?
I was working for some time on a programming language, and we are the Bentley type language, and we were trying to implement metaprogramming, the style of the elaboration monad and the TC modal in Agda. So we thought that if we could extend it for algebraic effects, maybe we could get a more composable way of doing metaprogramming in the Bentley type language.
Hi, April. Thanks
Hello.
for the talk. There's Sam Lindley here.
Oh, hello, Sam.
You mentioned, well, relating this to algebraic effects and effect handlers. Have you considered extending the simply typed lambda calculus to a language which itself has effect handlers in?
Oh, no, we have not. That's a good idea. That would be fun.
Thank you. Next question.
Hi, I wonder, so you choose type checker as the main demonstration, and there were papers using like applicative or monadic structure to implement the type checking and elaboration. So how would you like compare your work with them, like using hand?
So this is so we have a bunch of this work has already been used in languages like Agda and Idris, and I believe also in Rock. I think MTAC is has a monadic approach. The idea is that by using algebraic effects, you could choose to use your handler. So you can choose to use type checking or elaboration by choosing a different handler, and that's where we believe that this approach can bring us further in the process of using metaprogramming, because then we don't have to, theoretically, we wouldn't need to write a type checker and a elaborator separately. Yeah, I hope that answers.
Any more questions? Okay, now let's thank the speaker again.
Thank you so much.
The second talk, characterizations of partial well-behaved lenses. And the talk will be given by, can she? Oh, you use that or this?
Thank you. Thank you for introduction. So today, I'd like to talk about the characterization of lenses, which is used in bijunctional transformations, and when its get and put functions are possibly partial. Before I talk about our studies, I'd like to introduce a notion of the bijunctional transformation and the lens. First, I would like to briefly explain the bijunctional transformation, referred as BX, with a specific example. So this table has the past 3 PEPM locations and the number of presented papers. As you can see, this table has an obvious mistake, but let me go forward and explain. From this table, we can extract a small table of PEPM locations for the past 2 years without the number of presented papers. Now, I fixed the mistake on this small table. I desire to fix the problem in the original table by making modifications only to the extracted table, because the original table may be too big in actual case, or other people may try to update the original table at the same time. And BX had a method to update the original table with differences in the extracted table. This method is called put, and this is one of the motivations of the BX. In BX, the process of obtaining of a small part of the data is called get. Also, we denote the original data as a source and the extracted data as a view. In the most of the studies, S indicates the source and V indicates view. For the BX, Foster et al. Gave a novel approach, the lens. The lens is the pair of partial get and put functions. As I described before, the get function produces a view from the source. I think that's because it doesn't figure out. Oh, thank you. Thank you very much. The get function produces a view from the source. Yes. And the put function updates the original source with a modified view. However, we cannot define get and put functions arbitrarily because the get and put functions should be consistent. The most important consistency of the lens is well-behavedness. The well-behavedness is formed two properties, get put and put get. And these properties are called lens laws. Note that there are other lens laws, and we consider the other 5 laws later. Get put states that the source is not updated if the view is not changed. This is get put. And put get states that an updated source find view generates the same view. Updated source generates the same view. These laws are also originally defined for partial functions by Foster et al. But these definitions you can see here are for total functions. For clarity, we use the circle symbol for the laws for total functions in our study, like these circle symbols. There's an interesting property about well-behaved lenses. Several put functions may exist for the get function, forming a well-behaved lens. But it is known that the get function that forms a well-behaved lens with the corresponding put is uniquely determined if it exists. This is an important property in our study. So let's move on to the characterization of the well-behaved lens. This map shows the implications of lens loads with other loads. For example, when the lens satisfies get put, the lens also satisfies source stability. Also, when the lens satisfies both source stability and view determinations, the lens satisfies put idempotency. These 5 laws in the right half are specifically defined on the put function. I will introduce them later. And let me add some yellow squares. The purple squares for lens loads for well-behavedness, and the yellow squares. Okay, yes. Okay, it's okay. When the put satisfies all the loads in one of the yellow boxes, all lens loads in the other yellow boxes are necessarily implied. In other words, these 2 yellow boxes are equivalent to each other. Fisher et al. Gave an interesting theorem. When put satisfies all the lens loads in one of the yellow boxes, the put has the corresponding total get function that forms a well-behaved lens with the put. Also, the well-behaved lens satisfies all 7 lens loads in this map. Therefore, the yellow boxes and the purple box are the necessary and sufficient conditions for each other. Now I introduce the loads for source stability as an example of the other 5 loads. Source stability states that any source has a view update that does not change the original source when it is put. Fisher et al. Proved this theorem with the following statement. For the sake of clarity, we present all the laws in terms of total functions. Some programmers find it easier to define partial functions for certain problems, and our results can be adjusted to this setting. But is it true? Let me consider the case when get is a partial function. Let us assume that the conditions also follows for non-total functions. Obviously, a well-behaved lens satisfies source stability and the put get. From source stability, any source has a view that do not change the original source when it is put. Then from put get, any source produces a view. This is here. The get is defined on any arbitrary arguments. Defined on S. So we assume that the conditions holds for non-total functions, but this get cannot be partial. So this is a contradiction. This contradiction motivated our research, and our main purpose is to consider this problem. Furthermore, our study may be helpful in other ways. So there are some programming languages made for and used in BX. For example, Beagle is one of the languages and is implemented with the consideration that the original lens is defined for partial functions. Our study may help us to check whether these languages can express all well-behaved lenses or not, regardless of the totality. So in our paper, we aim to characterize lenses consisting of partial functions as Fisher et al. Did. Before the characterization, we define 5 lens loads for partial functions. After that, we characterize the partial lens in 2 cases. One in the case, only the put is partial, while a get is total. In this case, we show that the similar conditions given by Fisher et al. Hold. The other is the case where both get and put functions are partial. In the latter case, we show that the similar condition does not hold. Therefore, we introduce a new lens law and discover the new conditions with it. I'm going to divide the rest of my presentation into 4 parts: the definitions of lens laws for partial functions, the relations among lens laws with a partial put function, and then the characterization of lenses with partial get and put functions. I will conclude our paper at the end of my presentation. First of all, we have to define the lens laws for partial functions. GetPut and PutGet are originally defined for partial functions by Foster et al. Thus, we defined the other 5 lens laws for partial functions for our study. These are the definitions for getPut and PutGet given by Foster et al. The upper definitions are for total functions, and the lower for partial functions. You can see the down arrow symbol in the definitions for partial functions. This is the down arrow symbol. So this symbol means that if the left side is defined on the given arguments, it will be evaluated as the right side. For example, this get s down arrow v, this get s down arrow v, mean that if the get is defined on given arguments s, it will be evaluated to v. So this get is a possibly partial function. In the original definitions for partial functions, the functions are considered to account for the cases where functions are undefined on the given arguments. We defined 5 lens laws for partial functions. So stability for partial functions is simply change the equal symbol in total to down arrow symbol. And view determination states that when some views are used in update arbitrarily source, if the updates are successful and the updated sources are the same, the views are also the same, regardless of original definitions, original sources. Put subjectivity states that any source S can be successfully obtained by the put of some pair of the source and view. And put injectivity requires to any source S that when S is successfully updated by some views and the updated results are the same, these views must be the same. These views must be the same. Put and impotency indicate that the source remains unchanged no matter how many times the source is successfully updated with the same view, with the same views. Put and impotency is called put twice in other researches. These 5 lens laws we defined these 5 lens laws for our studies. Now, I would like to explain the implications among lens laws. I chose an example way to prove implications and characterization of lenses in the case only the put function is partial, while a get is total. Let me show an example proof of the implications of lens laws. The conjunction of source stability and view determination implies put idempotency. Please note that these 3 lens laws are defined only on the put functions. First of all, this is the definition of put idempotency. Our goal is to derive the consequent part of put idempotency from the assumption part of it, subject to the condition that a partial put satisfies both source stability and view determination. Thus, I begin from this term, the assumption part of the put idempotency. From source stability, any source must have the some views that do not update the source. Thus, we can add this. This term. The source S prime has a view prime, which do not update S prime. Next, the put also satisfies view determination. Since there's same S primes here and here. Oops. Since there is the same S prime for the 2 terms, we can derive the equation V equals to V primes. Yes. By substituting V prime for V in this term, in this term, we can derive the consequent part of put idempotency. Finally, the implication is proved. I explained the way of considering the implications among lens laws, and there are other implications. Now I explain the characterization of the lens in the case only the put function is partial. This arrow is the implication just we proved. Also, get put implies source stability and it implies put surjectivity. Similarly, put get implies view determination and it implies put injectivity. In addition, the conjunction of put surjectivity and put idempotency implies source stability, and the conjunction of put idempotency and put injectivity implies view determination. And now let me add some boxes. The purple box indicates the loads for well-headedness. The yellow box is corresponding to the conditions given by Fisher et al. The yellow boxes are also equivalent to each other. When only the put function is partial, we obtain a similar condition as Fisher et al. Did. When the partial put satisfies all loads in one of the yellow boxes, the put has a corresponding total get function, forming a well-behaved length with the put. However, what if we consider the case when both get and put functions are partial? This is the most important question in our study. Now, in this part, we consider the case both get and put functions are partial. To come to the point, we show that the similar condition given by Fisher et al. Does not hold. To remedy this problem, we introduced a new lens law and found a new condition with it. This is the same map I showed just now, but the implications from get put to source stability requires the get function to be total. Therefore, when we consider the case both get and put functions are partial, the similar conditions as Fisher et al. Does not hold. To remedy this problem, we introduce a new lens law named weak source stability. As the name implies, the new lens law is a weakened version of source stability. Source stability states that any source has a view updates that do not change the original source. Yes, this is a source stability statement. In contrast, the new law weak source stability states the same conditions for particular sources that can be obtained by input on some source and view. We investigated the relations among this law. Get-put itself cannot directly imply the weak source stability, but it's possible to imply at the conjunction with the put-get. It means a well-behaved length satisfies weak source stability regardless of whether the get is total or not. The other implications are also shown. Add all other implications among them these laws. As before, let me add some boxes. The purple box indicates the laws for well-behavedness. These yellow boxes are equivalent to each other. Also, these yellow boxes indicate conditions on the put. Similar to the theorem given by Fisher et al., we show that when the partial put function satisfies all the laws in one of the yellow boxes, the put has a corresponding possibly partial get function, forming a well-behaved length with the put. I'd like to stress this theorem. This is the most important result of our study. Now, I conclude my presentation. These are major related works. The original definitions with partial get and put functions are given by Foster et al. The definitions of get put and put get are also given in their work. In our study, we followed a similar way to define the other 5 lens laws. The conditions on the put to have the corresponding get is given by Fisher et al. This is the main question of our study. And we follow the way to characterize the lens laws and illustrate the map implications among them as Nakano did. And let me talk about further work. We showed that the put idempotency and put injectivity are enough to form a well-behaved length. The computational models for both idempotency and injective functions already exist. By combining them, the computational models for all well-behaved lengths may be obtained. And this model may help us to check whether the programming languages used in BX can define all well-behaved lengths or not. Another further work is to illustrate the bigger map, including other lens laws. This figure indicates the implications among 12 lens laws when both get and put functions are total, given by Nakano. And this is the map when only the put is partial. Some implications do not fall for this case. And this is the map when both get and put functions are partial. Certain lens laws, among certain lens laws, including weak source stability. Finally, I'd like to summarize the main findings of our study. First, we defined 5 laws for partial functions, and then we characterized the well-behaved length with partial functions in 2 cases. One is the case only the put function is partial. In this case, we show that the similar conditions given by Fisher et al. Hold. The other is the case both get and put are partial. In this case, we show that the similar conditions does not hold. Therefore, we propose a new lens law named weak source stability and prove new conditions with it. And thank you for attention. This is the end of my presentation.
Thank you for the talk. Questions? Okay, well, actually, I do have a question. I'll start. Oh.
Thank you. Very nice talk. So because I also do research on BXs, so I actually have always encountered some similar questions from outsiders that I find very hard to answer myself. So I like to hear your opinions on it. I think one of the common questions is that the round-trip properties, the put, get, and get put laws are not enough to guarantee meaningful bidirectional programs, because it only guarantees the condition where the view is not modified, and it says nothing when the view is actually modified. And so it's often requested that we add more stronger conditions to guarantee that the program we write are actually meaningful for practical purposes. So yeah, I like to hear your opinions on this.
So honestly, I'm not so much familiar with all four BX because I just learned the lens laws for other laws implications. So honestly, I've never heard such opinions that these laws are not so much strong. So
so I guess I can elaborate on maybe on this graph. So you see that the put-get law requires that the get-put law requires that you are using the same v to put back.
Yes.
And you get an s prime which is equal to the original s.
Yeah.
But it says nothing when we have a delta v on that v. So we actually put a v prime and we get an s prime.
Yeah.
There should still be some guarantee on how different the new s prime with respect to the original s, right? So it's like if I perform some small edits on v, there should be a small edit on s. So I was wondering if you have ever explored this possibility of additional lens laws to characterize these additional properties.
Is this the strong get put, right? No? I remember that there's a strong get put as a lens laws. Sorry, honestly, I don't remember the correct definition of strong get put, but you mean does it? Did you mean that?
I'm not quite sure if it is enough for those concerns, but yeah. Okay, yeah, thank you.
Any other questions for Asma? Okay, I mean, this is a general question too, right? This is the well-known view update problems in database, right? So I wonder, I didn't follow most recently, what's the state of research in the database community on this?
So sorry, I couldn't.
Yeah, so the problem you're addressing in database is called a view update.
Yes.
Right? So they didn't study it, or how did they study these properties, these problems?
How
do they not have partial puts in database, right? Do they not have partial put?
Yes. So the reason why we consider the partial get put functions, right? You asked yes, right?
Yeah,
so
I'm just wondering, I mean, in database, do they have this problem, right? How do they address it?
So how do I see it? So I think that there may be a partial put for database because like this example, so if we change everything in the small table, so there's no updates to this table. So the put may be partial. So did you ask how to address the partial functions in the table database array?
Yeah, yeah, one, yeah.
How to address partial functions? So we consider in this before our study. So we consider there may exist a partial put in the database, but partial get is difficult to consider in the realistic database project. But like this studies, so partial get may not exist for real database, but so we consider the partial get and put function for this problem because there may be to consider the computational models for get and put functions and verified length. So in consider this problem, get and put may not be total. Some lenses may be partial to consider all verified lenses. So this is why and how to handle the partial functions, the problems.
Yeah, because they're arbitrary functions. So you
Yes.
can have the problem. And of course, for real application, they try to make it total and all that stuff. Okay.
I am closer, so I can answer some the part of the questions. Actually, as far as I know, SQL, even SQL is a Turing complete actually. So in that sense, it can be partial. So it is one of the motivation of our research. Thank you for your question.
Thank you. Any more questions?
This is a question related to the question asked before. Why do you specify those two rules as the well-behaved lens? I mean, more generally.
Generally.
Is there any reason to pick those specific two rules, get put and put get, for the well-behavedness of lens?
So well-behaved is one of the we consider one of the most important consistency. I know that there are other consistency class questions, but lens laws so I forget the names. Are very well-behaved or other laws. So, but the Fisher et al. Gave this theorem. So this theorem. So we consider this problem because this is why we consider these problems. So, is it correct answer?
So is it basically because Fisher considered those two pair as a well-behavedness of lens?
Yes. Fisher gave this theorem, and we consider this.
Another related question is that do you consider any other ways of lens-like families, when the get is non-deterministic, like get or put is non-deterministic? So it gives you a different result, like it's not even a function. Do you ever consider that kind of related family of lenses?
Related families of lens laws. So other 5 laws. So other lens laws.
Yeah, I mean other lens-related types.
Other related types. So we consider just a symmetric lens, and I think that we consider the most basic lenses, and we didn't consider other lenses. Just we consider these lens laws.
Okay, yeah, that's a very hard question. Non-deterministic. So, yeah, okay. Let's thank the speaker again. Okay, so next we have this really anticipated, exciting panel. So we can bring 4 chairs for panel members. Okay, in the front. Okay, put this on the side. Just take the middle, yeah. And you have to pass this speaker on, like this one. You can leave one there. Yeah, Sam, you can leave one there. It's easier for people. Yeah. Yeah, sure. Anybody against recording? Up to them, of course. right? It's okay to record this, right?
Turn the projector off.
Turn off the projector. Turn off, yeah. It's done for today anyway, just power off. Okay, perfect. Okay, we have only this one mic here. Okay. It's perfect timing. So, and I'm introducing, you guys know all our three distinguished invited speakers for their exciting talks, but I also have Sam Lindley, who of course run the session and ask great questions. So that's our invited panelists for today. Okay, and the victims for these really hard panel questions. And so actually I will start with actually reading a question first. He's one of the great minds and started work on this called the binding terminology for partial evaluation and lots of other fundamental work, especially really hard type reference for really hard type systems. Okay. So yeah, I actually shared this with some people. Okay, so this is by First Hangland. Okay, effective neural symbolic AI. Essentially, the old-fashioned symbolic second-wave AI from the 1980s, combined with the du jour statistic and differential third-wave machine learning. Okay, like now is expected by many to be required to move AI beyond the LLMs and the current trend. Which role can modern semantics-based techniques for manipulating programs play? So of course, presumably as part of the symbolic side, of course. Or that's the question, is the very notion of rigorous context-dependent semantics based transformations outdated and useless in programming now? So anyone want to start, or I would just pick up victims in order? Really hard questions, and this is covers all. I spent a long time trying to formulate this question, right? And finally, first, I decided to ask the steering committee, and here pops this great formulation, so I just use it. And anybody can also think of a follow-up questions. I have a few. Okay. How about Sam? Okay. Just use it.
Let's just use the handle. We only need one at once anyway, don't we? I'm not quite sure why I'm on this panel, but yeah, interesting question. I have seen the question already, but I'm not sure I have a good answer. I think probably, in common with several of the other panel members here, I'm rather skeptical of this whole direction. I certainly don't think what we have nowadays in terms of LLMs is really posing any risk to a lot of the kind of work we're doing. LLMs seem pretty terrible at program manipulation. They can do something, but then, well, you have to check that it isn't complete nonsense afterwards. So, yeah. Does anyone else have a better answer?
Okay, so turns out I have lots of opinions about inference. Even inference I haven't done before. But I have looked a lot at LLMs, done some experiments with program manipulation, and I think, like Sam was saying, they generally produce nonsense. So the only uses that I've seen that have been sort of halfway productive are combining old school techniques, things that have embodied semantic knowledge that you then use to check the output, right? So for example, F-star is using these to try to generate proofs, but then of course they're in a dependent type system, they check the proof, right? Which involves semantics. So at the moment, I don't really feel like LLMs are a threat. I mean, I appreciate the provocative question, but I don't think it's like going to throw out all of our work. I think what's interesting is how often LLMs produce anything meaningful at all, which suggests like they're just statistically generating text, right? And there's a lot of text you could sample. The fact that they produce meaningful text at all is surprising, and the fact that they produce it kind of more often than not is very surprising. And that suggests there is some semantic knowledge in there somewhere. And I feel like we should be doing something to try to extract that and compare it to our very hard, like very rigorous semantics that only produce the things we have told them to produce, but always produce something meaningful.
Well, I mean, Fred's question is quite loaded, right? It's clear what he. I'm going to repeat a little bit about what William said. So I design hardware. So and sometimes I design hardware in this language called System Verilog, and I use Visual Studio, I use Copilot, and I do say make me an address generator which works like this, etc. But I also write these System Verilog assertions. You saw a flash of them in my talk. These are basically like LTL logic, but it's part of the System Verilog language. So I write the properties that I believe should be true of the generated circuit. So VS Code will generate some System Verilog, and then I run the model checker on it. It gives me a counter model. I give the counter, it's a conversation. I give it back to a VS Code, and it fixes that error, and we keep iterating until the circuit as we generated passes all the properties. So it might still not be correct, but I'm in much better shape than I was before. So this is just the tip of the iceberg, and I think LLMs and where they go, and all the work that we do with semantics and transformations, these are things that we're going to use in concert with each other. They're going to magnify each other's capabilities and power. So I'm actually a bit more optimistic than Fritz. Next time I see him, I'm going to have a beer with him and try and convince him.
Yeah, I think I have much to add. I think I'm also surprised how good they are in many scenarios. Especially when I see students use them in courses. But I think it is important that we specify why or extract the specification out of a question to an LLM, right? Because once we have that specification, we can actually in some sense test whether that program or that transformation satisfies these kinds of properties. So it goes in the direction of what Satnam was saying, right? You have these kinds of properties in your mind, and then you use actually the model checker to verify these properties, but then you bounce it back to the large language model to generate maybe more different examples that would maybe satisfy these properties. But ultimately, I think it's sort of in concert with what we're doing. But I think in general, probably we should maybe teach students more to specify properties rather than write programs, because I think it's hard actually for students to assess the correctness of the program, right? So they use them sort of naively. And I guess it's sort of that's the easy way, right? It's like you just ask, can you generate a program that satisfies blah blah blah? It's like a homework description, and then very often it is right, okay, but sometimes it's not, and it's much harder for a beginner than to assess whether that solution is right or wrong. And they don't have the right tools to assess whether it's right or wrong. So I think what our community can bring is sort of tools to assess whether these answers are right and wrong. And for that, we need, in some sense, specifications.
Thank you all. It's already more impressive than expected. Even start with Sam, because lots of us, some of us at least, have the same feeling as Sam has, right? Just didn't formulate, so he spelled out. And as they go, they each have to think more, what new and more, I should say. And I think really new things come out of this. So if I want to just summarize a little bit, but well, for one thing, I do want to emphasize, okay, what Satnam is saying is, I write the assertions, okay, and then get these LM to check. And Brigitte says, oh, we need to teach students to write that, right? So think about that. So, but to be more concrete, I have these couple follow-up questions. Okay, so we know LLMs hallucinate. That's why Sam isn't impressed. Or nowadays they try to make it have try to justify their bad answers or good answers and give you really long answers. I feel like I don't have patience to read and try to grade a student's homework, right? Just write a lot of bullshit. Anyway, right. But how can sort of we can still try to use it to help semantic-based transformation, and the semantic-based transformation may help reduce hallucination, right? Is there some thought about how we could do that? By the way, audience can also, anybody want to add to the first question, right, in general? By the way, the people can come in, either a couple chairs, let's put in here. Yeah, you can come in. Yeah, go ahead.
So, at the risk of severely embarrassing myself in front of 4th grade panelists, so a lot of the methods I see, a lot of method people propose about combining symbolic methods and LLM, I think falls largely into what I personally just say called the branch and bound idea. So the idea is you treat the LLM as a large random box. You don't know about the semantics, but it's better than a random text generator. You hope, at least you hope. You have to generate a bunch of stuff, then you use a formal method to bound it, to weed out everything that's not good. And our hope seems to be that, well, the LLM somehow has some sort of understanding, at least for whatever method, about the semantic space that's working in. So it will generate higher quality, a random text of strings that we have, so the chances of having something that actually works after weeding out is higher. Is there a way to not do this dance? Is there a way that we, PL people, can sort of start to enhance the ability of LLM to actually effectively explore the semantic space, instead of doing this, trying to rein in a wandering child style of work? Do you think there's a possibility to more directly engage with the semantic space of LLM?
Hard question. Go ahead.
So I'm happy to respond to that and respond to something you mentioned about hallucinations, which is my first thought is that hallucinations don't exist. Because to say that an LLM is hallucinating is to say that it's producing something that's invalid. But hallucinations are indistinguishable from valid output. All the LLM is doing is producing syntax, right? And there's no way, we as a human look at this syntax and we impose some meaning on it, but there's no way to give a type to an LLM and say, oh, these hallucinations are ill-typed or something, right? There's no way to distinguish these two outputs. So I object to hallucinations. LLMs don't hallucinate. They produce syntactically probabilistically valid syntax. The interesting question is, why is so much of that syntax meaningful, right? It's more meaningful than randomness would suggest. And so we sort of hope that either we can figure out the underlying semantic model that the LLM has learned, or we hope that we can use this probabilistic space that is better than random in some useful way. A lot of work goes into looking at this as a source of better than randomness as a probabilistic space. So for example, the fuzzing community has looked at LLMs as could we use these for fuzzing better than random? And it turns out in some cases, you can't. Actually, randomness is just better. And it's better on a lot of dimensions. You can find more of the things you're looking for, more bugs, and you can find them cheaper than using an LLM. So in many cases, despite the fact that it seems like it should be better, random is actually better. If we actually want to understand LLMs, what we do need is some way to try to interrogate what has the LLM learned semantically. Why is it generating anything semantically meaningful at all? And what is the underlying semantics it has learned? And I don't know how to do that yet. One of the things I think is old AI was focused a lot on reflection, on sort of self-understanding and reflecting on what the system itself knows and understanding itself. And this has not come up in the kind of new LLM space. And it seems necessary if we want to be able to interrogate what the LLM has learned, more than just look at its output, which is statistically generated syntax.
So I'm definitely not an expert in this area at all. But one thing, your question about how can PL help in this domain, I remember going to a talk, it must have been 10 years ago, before the whole sort of big thing about LLMs and so forth. And someone had an example where they were trying to teach a simulated racing car to drive around a track. And they'd started off, they had a perfectly round track, and they were just doing random perturbations, and I think it was going through some sort of machine learning system. And it managed to kind of go around the track in a sort of rather wobbly way. Then they gave it a different track, and it just crashed immediately. Then they rephrased the system in such a way that the movement of the car, rather than being some sort of continuous thing, was specified using a little DSL. And they learnt how to instruct the car to drive using the DSL. And it drove perfectly round the circular track, and it drove perfectly round this other track. So I don't know what we need to do, but somehow combining some knowledge about domain knowledge about the structure of what we're trying to learn with these technologies, maybe that will help.
There are competing thoughts in my brain at the moment. Yeah, I mean, I think I agree with William, really. Like, right, what it's generating is sort of statistically generated text. And so you could think, of course, saying, okay, you know, by like make certain choices heuristically in what it prioritizes in the next word or next sentence, or, you know, maybe we could use some kind of type checking in between before it outputs some kind of syntax. Okay. But it seems that they have empirically found sort of this great randomness, or I think it's a particular factor which I forgot, by which they kind of prioritize, like pick a certain element of the next prediction, and it seems to work very, very well. Okay, and so I don't have a lot of hope in some sense to add in directly sort of this semantic knowledge at these given points. I mean, also I think it's sort of probably has sort of escaped almost our sphere, right? I mean, because these models are very large. Who is by now implementing these models? Can a researcher actually implement their own model? You know, somehow I don't think that's a viable research direction to explore. So that ends up with, in the end, sort of saying, okay, they produce syntax, and we'll just accept that they produce syntax, and maybe we can figure out what the rules are that they have been doing. So we have used large language models to do type error prediction, okay, and for OCaml programs. Okay, I first thought that was the most craziest idea ever. So I came back from a vacation, and there were these 5 students who tried to use type error prediction, and they used these large language models to do that. And they had surprisingly good results. So they wanted to identify the true source of the error, okay, rather than OCaml doesn't give you the true source of the error. It gives you, it computes some constraints, and it fails at some point later, okay, and that might not be the true source of the error. And so it turned out in that case, they did want to know, like, did it learn some particular structure? And it did seem to have learned some structure. It didn't learn any formal rules, okay, that would correspond in any form to our typing rules. But it did seem to have learned some structure of these programs. Now, I don't know if that really translates, because a lot of it has to do with the data they are trained on. And so, you know, they work very well on languages like Python and Java, but if you have like a low resource language, and funny enough, OCaml already counts as a low resource language, then how does that actually translate, right? So we don't really know. Okay. And so I think that begs sort of also the question, you know, how successful will large language models be in, for example, generating logical specifications? Okay, so there are some languages that are specific to model checkers, but there's not a lot of data out there to train these large language models on the specific language that a particular model checker would use, right? So then you can sort of say, well, okay, we'll introduce some kind of intermediate language, and then we'll do some translation. Then we're back in the PL game, okay? If that gives us better results, I think that depends, right? And there are mixed results in some sense out there, where sometimes it works and sometimes it doesn't. So I guess I don't have a real good answer.
Come back to what we call hallucinations. Well, hallucinations are creativity. That is what LLMs do. We just make a value judgment about some of the things that they create. I mean, we call them hallucinations. So I mean, I agree very much with what William has just said. I think it's remarkable what LLMs, when you fine tune them, can do. Right, like code. Like you've got the Llama, you've got the general Llama models like Llama 3, but then you have Code Llama that's been fine tuned, right, for coding. It's quite impressive. And we fine tuned for mathematics. You've got machine learning models that I think solve all these Olympiad maths questions. There's something going on there. I mean, I'm not a machine learning researcher. I don't understand, but it feels a bit more than tab complete, right? What's going on? It's quite profound. One of my favorite uses, actually, for these LLMs is I program a lot in Haskell, and Haskell sometimes gives you incredibly hard to understand error messages to do with some rigid variable A, etc. And it's the fact that I'm the world's first Glaswegian user of a Glasgow Haskell compiler. They still stump me. So what I do now is when I get an error like that, I just in Copilot ask it to fix the error or explain the error, and it's amazing how often it can actually do for Haskell, right? Not a super mainstream language. So I think there's something there.
So I wanted to come back to something both you said and that Sam said, that what's more impressive than LLMs in general is when you narrow the domain of the LLM to say code or to like a DSL. One of the experiments that I love doing with the LLM is I ask it to give me a budget, and I explain the budget in natural language. And what it typically does, it will return this as an itemized list. It's like, okay, here's your budget. But then you can ask it to translate to new abstractions. Like, okay, translate this to a markdown table, translate this to a CSV. And what's really remarkable is it will translate the structure and leave the data untouched. So it seems to have learned abstractions in a really fundamental way, better than it has learned like facts about the world, right? So what it seems to be doing very well is learning structure, and I think that's kind of reflected even in English text, right? It has learned the structure of English language sentences. It has learned the structure of code. It's also learned that it knows how to translate between structures. It can translate like the budget from an itemized list to a markdown table to a CSV to whatever representation you want. Now, it will fill that with things like nonsensical totals that don't add up, but it really seems to understand the structure well, which is quite impressive.
A slightly different direction, again, trying to connect with PL, is one could imagine really trying to formalize the language in which you write the prompts. So currently we just write English, but you can get quite a long way with prompt engineering. I mean, there's all this sort of jailbreaking and so forth that people did in order to get LLMs to do things that they weren't supposed to do. But maybe we can take that further. I don't know.
See the work of Eric Meyer. Follow him on Twitter because he's advocating using data log-esque structured ways of prompting in order to get much better results from LLMs.
Yeah, I just want to say, I mean, I totally agree that if we're going to be programming these systems, we should maybe design a language in which we can write programs rather than using something as ambiguous as English language text.
Okay, I see several hands raised, but just want to do one summary, right? And because first time somebody openly to me objecting the word hallucination, and he replaced with random. Although I think people probably don't think, I mean, really technically it's just statistically whatever comes next. But when there are multiple choices or equally statistically possible, that's sort of randomness come in, right? But I love this word that Sadavan said, called creativity, right? Something you dream up. Oh, Peter said that. Yeah, by the way, when the mic got passed back, and actually William has another word, nonsense, to characterize it. So I saw you were the first one who raised a hand. Do you still have a question?
Okay. So I was interesting what you mentioned, Sam, about using the DSL as like I guess almost like a back end to the LLM. Something this just made me think about that a not entirely uncontroversial idea in linguistics, the language acquisition device, like the Chomskyan idea we have, something in our brain that helps us learn languages. I'm just wondering if, like everyone has been saying about, having some sort of structure, that we program in ourselves based on what we know we want. Could this work? Is this a way to actually reconcile, the semantic things that we like and the statistics things that I assume machine learning researchers like?
Yeah, that's the question. I don't know.
So I think this kind of relates, and I don't know who is familiar with algebraic effects. I know Sam is for sure. But I think I watched one of your lectures, and you were talking about how algebraic effect handlers, what you program, if you're programming against the effect handler interface, you're creating a syntactic tree, and then the semantics of the handler define like a fold over that tree. And I'm just wondering if LLMs, if we split out the semantics and the control flow from the structure and the syntax of our programs, would there, do you think, or would you anticipate that they would produce better code or better able to separate the concerns of control flow and all of the different semantic nuances in behavior?
Seems like he's asking about the semantics.
Yeah, I think that's a very good question. I mean, it comes back to this idea that, well, the point that LLMs are just producing syntax. How do we, or if we have a natural way of programming in which there's a very distinct separation between the syntax and the semantics, can we leverage that somehow? Again, I don't know. Maybe.
Sorry for keep asking this question to Sam, but yeah, it's to do with the DSL part you mentioned before. As you said, I got what you said as giving some DSL improves some kind of AI in general. So, but as Bridget said, it's hard to do that kind of things as a personal researcher. So, in general, and not just for Sam, but for all four of you, do you think does it make sense to put some effort on the making some DSL as a community so that we can use it for LLM?
So I think what LLMs are doing is that it opens the world to generate programs to many, many more people, especially people who are not necessarily trained to be programmers. Okay. Now, so if you think back of how we started to use things like search engines like Google, we also learned how to phrase certain questions, right, to get good results. Now, for LLMs, if you want to generate programs, we also need to learn, I think, how to phrase good questions. I mean, that's sort of implicit in way right now, where we sort of use prompts to maybe improve the answer. But ultimately, I think it's a certain way that we're asking to solve for a solution, for a program transformation, or more generally for a solution. Maybe the way we kind of split up a larger program, because we know they're sometimes not that great to generate really large programs. They're better in generating smaller chunks of programs, although they may get better. Or you know, when William was talking about, I start with the budget and then I ask it for these transformations. That's already splitting up the actual problem, right? It's doing some of the hard work of splitting up where they want, what kind of result we want in the end. So I think the bigger question is how do we learn how to ask sort of the right questions, right? So that we get good results. And I think that has to do with sort of how we divide and conquer, so almost a problem, right? And how we kind of split up the problem in smaller chunks. Well, I think you can think of this as a DSL, if you like. Okay, I mean, it's basically, a structured way of asking the questions. And what is a structured way of asking questions? I mean, it is in some sense in DSL. It's maybe close to a natural language question, this DSL. But I really liked Andy Gordon's talk at, I don't know if some of you had seen at ICFP this year. So where he quoted Grace Hopper. Okay, so Grace Hopper was one of the first compiler writers, if you like. And she had this dream, right, that people would communicate in natural language. The idea is they wanted to implement. And that was in some sense how she ended up designing Cobalt. But now, okay, you can actually ask in natural language the LLM for a piece of code. And so in some sense, you might say, well, haven't we achieved this dream, right, of generating programs out of a natural language specification? Yes, the natural language text is not precise, right? But it does generate often what matches our intention. And maybe we need to communicate our intentions better, right? Because as William was saying, well, maybe it's not hallucinating, right? It's just creative in what kind of results it will get. But we need to then decide what was our intention, and we'll pick the right result, right? But that problem is really that we need to be clear what our intentions are, even if we decide, right, to accept a certain answer or not.
Sure. I mean, I'll just answer a different. I'll just follow the example of a Republican and Tory politicians and answer some other question that I wish I'd been asked. Being a idealistic dreamer, I've always wished that the way we wrote software was this University of Oxford 80s style of stepwise refinement, where you start off with a specification and then you refine it, but maybe in your theorem prover, step by step with proved correct transformations to get some efficient implementation. What a wonderful concept, but it only ever worked for quite simple programs and required people with PhDs at Oxford to do it. But maybe now we can do it, right? Maybe now we can democratize these kind of proofs, and we can have a co-pilot that could do all the kind of tedious steps. And now we can maybe take realistic programs, start with their specifications, which is the great bit of creativity that the humans bring to the table, and then the machine helps you with the video game of doing all the proofs and the sublemmas, driving that spec to an efficient implementation. I think that's the kind of crazy thing that I think that wasn't viable before. Maybe that is now becoming is possible viable because the LLMs is now can take care of the details, and more people could use technology like that.
I think something that's come up a few times, and particularly there, is this idea of a dialogue or a conversation or interactivity, and that certainly seems like a very powerful way of developing software. And we already have been doing that for years with proof assistants like Coq and Agda and so forth. But we don't get very much back from them. They just sort of say, "These are all the types," or "This is wrong," and you. More or less, all of that creativity has to come from the human. But if we could make that more powerful, then yeah, I think that's a great idea. But I don't know how viable it is.
So I think one of the things that's very powerful about LLMs, which Brigitte and Satnam mentioned, is they democratize generating things that are otherwise quite complex. So generating code requires a lot of training. Generating, say, digital art requires quite a lot of training. And they make it very easy. And the hard part becomes, well, what they're doing is generating something from an ambiguous statement, right? So what they seem to be very good at is handling ambiguity. The downside to that is, well, if you've given an ambiguous statement, it will generate something, but it's of course unclear if it's what you meant because your statement was ambiguous, right? Because you were expressing yourselves in natural language. I think that's probably why, as we move to more formal languages, they get more precise, they get better. if you tell it, well, generate a markdown file. Markdown is quite rigid. There's very little ambiguity in what a markdown file looks like. Although it will get all the data wrong because there is a lot of ambiguity in what the data of a markdown file is. I think that handling of ambiguity is very interesting to me. And one of the one of the failure modes is like you say, oh, generate a program in my favorite language, Racket. And it will sometimes do that, and it will sometimes generate totally invalid syntax. But the same is true if I tell a 110 student to write 110 is our intro programming course. If I tell them to write a valid Racket program, they will often write invalid syntax, right? So it is performing a task that has a lot of ambiguity in it, and it's performing about as well as maybe a first year undergraduate, which is quite interesting. And what we seem to expect of the LLM is something we would never expect of a student, which is it should always perform perfectly. I don't even expect that of myself. I write invalid syntax sometimes, right? And what we haven't figured out how to do is integrate this system that acts very ambiguously, doesn't always generate perfect results into our other systems where most of our computer systems we do expect to behave perfectly, right? We feed a program to a type system and we expect it to just check the rules systematically. And that's because it's something we have a lot of trouble doing ourselves. And I don't think we've figured out how to bridge this gap. But I think if we're going to try to integrate LLMs into something like PL, that is where it ends up being like, we need to interact with the LLM with all of our other deterministic tools in the same way that a human is interacting with these deterministic tools.
Sure. Thank you. I saw a couple of hands raised. We have only 10 minutes left, Barry, and one last. But I actually had one last question, and someone already answered, right? But we do that afterwards, like between this thing finish and whatever the Jane Street people want to go, which is what are your experiences trying LLM to do program transformation, not just do programming. Okay, so I won't ask that question, but it's fun. I did try. We're preparing the questions. Okay, but I have one most important question I will ask, and then they can ask, and they can choose what to answer. Okay, so basically, actually, Sadna and Brigitte indicator I've emphasized at the beginning, right? You get, now say, okay, I'm hallucinate or nonsense or creative, whatever it is, okay? But the point was, well, how do we make sure something was at least more reliable? So program verification, that's one of the biggest things this community has been studying, okay? And in fact, verification, sure, here's a program, but you need to verify against something, right? And people are already saying, separate DSL, whatever you intend. And so in fact, even at the Daphne the day before, the workshop, right? And people were saying, Daphne, right? That's the one verify against invariance. And say, where do you generate invariance? Oh, we also use LLM to generate invariance from English to invariance and from English to code and verify. But those invariants are right? So how do we? So indeed, that's Satan saying, I write specification, I write invariance, and that's what I want, okay? But he's highly capable of doing that, and Brigitte is saying, let's teach students to do that instead of writing low-level code. Of course, Satan followed up, if we can do this stepwise refinement even automatically, then we'll never have to write the lower-level things, okay? But that's your question. So how do we do that, right? How to teach them?
My belief is that these LLMs are capable of doing all the craft work in the world, and the truly creative stuff is what will be left to us. But I think we can test this hypothesis in the following way. We often give a talk or write and we say, and now this step is done in the usual fashion. Yeah. So I think it might be interesting for all of us, whenever we're tempted to write that or say that, to actually think, can I get a machine to do this stuff in the usual fashion or not? And that gives us quite a spread of possible test cases beyond the things you might think of without any background. You're doing something rather complicated and you think, well, I'm just going to use the techniques from this paper. Well, if you give the machine the paper and say, do the usual thing, it would be interesting to see what comes out.
Okay, let's get the last question, and then I said they can choose and we'll finish.
Hello. So I'm kind of curious if, kind of on the theme of like accessibility for people without technical training, if the ways in which people use LLMs have influenced your thoughts on language design, because I think we've seen a lot of people using LLMs for trying to teach themselves something new or trying to debug errors and whatnot. And yeah, I'm just kind of broadly curious about how that plays into programming language design in your head.
So I have two thoughts on this. Okay, so I think where I've seen that non-programmers, non-computer scientists are generating code is, this is an anecdote, okay, my neighbor actually runs a shop, okay, where she also has an online site where she sells various items, and she needs to update the description of these items, okay. So for that, she actually needs to generate some HTML code, okay. And she uses LLMs to generate these kinds of little blurbs, which are little descriptions, as well as the HTML code that she needs to put there. Okay. And I mean, for that, I think it's a very viable thing, right? It makes her life easier. She's more productive. It's easier to update these websites and keep them so that they show up in the Google search engine quite highly. Okay. Now, for teaching, okay, so I'm teaching a functional programming course, and now last semester, I would say everyone used some large language model, okay, to generate the homework assignments where they didn't get any didn't get any credits for. And I have a student who ran all our homework assignments through through a series of these large language models, okay. And it turns out, yes, they vary a little bit in the code quality, but you know, they're very, very good. They would get basically an A- on all of our homework assignments, okay. Now, where large language models were not good in some sense, or were at least misleading, was in teaching concepts. Okay, so I also gave students some kind of conceptual questions. So, for example, generate an example, give me an example to highlight the difference between overriding and overshadowing. Okay, and as Annie was saying, right, you get the large language model generates a very long text. Okay, and the text might even have some good ideas. Okay, but it can also be completely wrong. And for students to assess, right, whether the answer is right or wrong, that is really, really difficult because they're just learning something. And so they have no reference, right, of comparing it to. So you can only really assess whether the answer is what you wanted or what the teacher wanted in this case or what this concept really meant, right, if you already have such an idea in your head. And so I think that is sort of the difficult part, right? It's much harder to understand something is not right. And that's for a novice. How, right? How would you do that? You need a sort of a trusted source that you can sort of rely on in order to learn new concepts. And so I'm a bit more skeptical essentially about sort of in the context of teaching and learning, right? What kind of role they actually can play. They certainly can play a role like of fixing type errors, what Satnam was saying, right? So I think students do that as well. Fixing syntax errors, fixing type errors. But it's almost like a drug, right? And so, yeah, it's easy, right? So then my question is, okay, if you don't, so I think Barry was saying it's a craft, okay, but in order to become sort of you know, masterful in a particular technique, you need to learn a craft, I think. You need to learn the craft first. So my question is really like, how do you teach people still the craft, although they might not need the craft, right? See what I'm saying?
Coding is dead. Long live coding. So we see people use LLMs to make nice web interfaces. Lots of React code gets generated for you. I bet you almost never do you get exactly the right React code. So then you have to fix things up and get exactly what you want. You needed to have been a competent programmer. You needed to understand some basic principles of React and how it works in order to be able to do that kind of fix up. So LLMs are acting as a magnifier for your productivity as a programmer, not as a replacement for it.
I just want to comment on this idea that if you're doing the usual thing, then LLMs can be quite good at that. And that's sort of what, so in my compilers course, this is, we ran a bunch of our assignments through the LLM. And after explaining like how they usually go, the LLM is quite good at generating something that's close to a solution. It's not very good, but it was enough to convince me that almost certainly all of the students will do this. And that means I can't rely on reading their implementation as a good assessment of what they've learned. Instead, I need to figure out, do they understand the creative aspects that go into the compiler design? And so we shifted away from purely assessing them based on the code they have implemented, and tried to figure out how do we assess them on whether they have learned some creative aspects that they could then explain. You then go and implement this in the usual way, right? So now our final has a bunch of questions about, okay, suppose you want to extend your compiler, which of course you've implemented merely as practice. You could have used an LLM to generate it, but having actually implemented it, you will have also learned some concepts. Now, what would happen if you wanted to change the design to work this way? And all they have to do, they don't have to write any code. They have to explain that design and then tell us like, oh, and you would implement this in the usual way and that in the usual way, following the standard design. Right? And so far, this seems to be working well. We'll see at the end of the semester if it works perfectly. But I think shifting away from thinking of demonstrating that you understand something by following the usual pattern to inverting that and say, okay, do the creative bit, and then you're allowed to use an LLM, that's fine, to do the usual thing, right, the easy thing.
So what Brigitte said just reminded me of one of my own anecdotes, which is kind of inverted from what you might expect. So a couple of my undergrad students were doing projects involving effect handlers. And my postdoc was helping to supervise them and read some of the text that they produced and said, this looks like it was written by an LLM. And I'm pretty sure it wasn't, because I asked the students and said, did you write this or did you use an LLM? And they said, no, I wrote this. And I believe them. And I think, well, maybe that's capturing like part of the power of an LLM. What came up before, that they're pretty good at behaving like naive students who don't really know what they're talking about. This was trying to describe the difference between shallow and deep handlers, and it was a sort of plausible description of what that might possibly mean, but it was clearly wrong. But yeah, it was interesting that they'd not used an LLM, but had fallen into the same kind of traps. But yeah, perhaps this kind of trying to describe some really quite difficult technical concept seems to be something that LLMs are not very good at the moment. Whereas the kind of thing that Barry is suggesting, maybe we can have these sort of mundane tasks be done by LLMs.
Okay, actually I'll ask a last quick question for each of them. They just say one sentence, right? What should the semantics-based program transformation community should do in the age of LLM? And you have 1 minute to think. And I just want to summarize one thing was from what I heard, not the answer to that question was, right, the first scaring question. And from what I just heard here, and of course I seen before and thought before, was LLM, they're exactly complement to what semantics-based program transformation doing. They're not going to replace us. Right, started with Sam saying, I don't think they're going to do it, and I think all their argument supports that. But now they have to ask the question, right? The visionary tell us, what should we do? And
I don't know, but I think what is absolutely crucial, and this has come up several times already, is that whatever we do, we need to have ways of getting assurance for whatever the LLM produces. So as long as you're in a setting where you can easily validate the output, then it's a really powerful tool. So thinking about how we get assurance.
Yeah. I think the thing I would probably do if I was spending much time at all on LLMs is try to extract what the LLM has learned in a way that I can be sure it has learned something. So try to get it to say, explain to me in a more formal language than English, what semantic transformation have you actually learned? Like, for example, the markdown to CSV. It has clearly learned something there, But if it could explain to me in formal language, I'd be more convinced that it has learned something meaningful.
Yeah, like Sam, all I know is about LLMs is how to multiply matrices fast. All this other stuff is above my head, so I don't think I have anything useful, meaningful to say.
Lost my train of thought here. Right. So I think what William was saying, I want the LLM to explain to me what it did. And I think that is actually, something very important because it allows us to check in some sense, right? If what it did matches in some form the intention of the programmer, right? Because and so there was an interesting talk actually in this talk by Andy Gordon. So they were generating Excel code from natural language specification. So the user who's not a programmer would say, I want to add, extract the first column from this sheet 5 and I want to add it to the second column or whatever. And you might not, people might not remember all these Excel code, but so it would generate some Excel code after various kinds of steps. But then the question still is, right? How does the user know that this strange piece of code matches what they had intended? And so the step they had added was essentially an explanation, to return an explanation or extract an explanation from that piece of code. And I think that is actually something maybe we need to think about more, how we can sort of have explanations of the code. So it's a way of us testing whether students understood the code, but I guess it's also a way of trying to understand whether the model actually understood what we were asking.
Okay, thank you all so much. Actually, if I use one word to summarize, like semantics, that's what's missing, and all of them actually come up with this beautiful conclusion. So I like to let's always thank the panelists the first time. And thank all the participants and all their questions, right? We should all thank them and thank them the second time. Okay, so that concludes PEPM this year. And really thanks everybody for all your contribution or interesting discussions. I saw they actually had to break them up during the break, so you can go ask this half hour before you go enjoy Jane Street. Okay, and see you next year in France.